Okay, guys, let's go ahead and get started. So we're going to be finishing up all of our domains today, finishing up domain 3 and covering domain 4. So we only got 1, 2, 3, 4, 5, 6, 7 slide decks in domain 4. Some of them are like a little long, but again, we don't really have to spend a lot of time on some of the things we're going to go over in domain 4 because a lot of its objectives we've gone over already or kind of talked about. So we just want to make sure we hit it one more time so we do get all the information for the exam. But, we've gone over SIME so much and like data sources we've talked about a lot. Some things we haven't, so obviously, but I hope you get the point that even though some of them may seem long, we've gone over a lot of this already. Okay, let me make sure I have my other side up. Let me bring up Academy. Not Security Plus. We need to go to SecurityX. All right, awesome. Okay, sorry, let me just get a few more things set up here on my other screen, guys. Okay, so going over domain 3.8. Given a scenario, apply the appropriate cryptographic use case and or technique. And in this section, we're going to be going over use cases. So everything in red is the exam objectives that we are going to go over. Okay, so data at rest. Something we've talked about a lot, but data at rest is something that is in storage, or it's stored. It's not currently being used or transiting across the network. Examples of this are file shares, storage area networks, databases, and any kind of media that's archived, any data that's archived. Now, and that's kind of describing a lot of the on-prem things, but in the cloud, we have cloud-based storage records. We have persistent data drives, or disk drives in the cloud as well. And then here it says virtual machine images. So, you turn your virtual machine off, that like data does sit somewhere in storage. You deploy ESXi, you have a data store where you upload your ISOs and your OVAs, and a lot of the VM files, like a VMX file, is stored in like ESXi. It's data store, and that data store may live on like a separate storage network or device. So that is true, but virtual machines could also be technically like data in use when they're on and they're running, and that could be looked at as something that needs to be protected. So virtual machine images and files is a little bit more accurate. Just want to make a delineation there. So the primary threats to data at rest include unauthorized access, device theft, insider threats, improper access control. There it is again, access control. It's always our big one. And compromised systems. So obviously, if you fall victim to a ransomware attack, you click that malicious link, boom, they encrypt your data drives, and now you're screwed. Hopefully, you're doing backups. One of the key ways we protect data at rest is encryption. So the primary cryptographic technique used to protect data at rest, that is encryption. Full disk encryption, and it's typically using a symmetric encryption algorithm. And then we learned about yesterday self-encrypting drives as well. So symmetric encryption algorithms are typically used because they are efficient and well suited for encrypting large volumes of data, and that's even true with data in transit, like we're going to talk about. Complement implementations of data at rest encryption include FDE, full disk encryption, database encryption, encrypted backups, and cloud storage encryption. And that's what we talked about, like you have some cloud-based encryption keys or customer-managed keys. So that's how we like to protect our data at rest. But along with that is just unauthorized access. We don't want to have any unauthorized access to our data at rest. And if we're considering like a laptop, phones, data, right? The data on there, that's data at rest too. And we protect that with full disk encryption, but also like mobile device management. And then we have data at transit. I like data in transit better. What do the exam objectives have? Did I type that right? Yeah, data in transit. I'm going to fix that right now. Data at transit makes no sense. This must have been when I was making these slides late at night or something. Okay, so data in transit refers to data that is actively moving between systems across a network. This is web traffic. This is just any network traffic. We don't need to dive into every single layer 7 traffic that could be attacked or data that we need to protect. It goes over the big ones here because that's like what's our biggest attack surface. When we're browsing the web, if we don't have the proper things in place, we can get man-in-the-middle attacked. Email communications, we want to protect our email servers, which nowadays is like, it's all in the cloud. So if you're running Office 365, no one's attacking that Exchange server anymore. That means they're attacking the cloud. So now what's the new attack vector? What's the new way to get there? Is identity access management, getting access to your Office 365 portal. Big file transfers, though. If you're doing like FTP over the internet, even if it's within your VPN, okay, we get it. From remote site to HQ, we have an IPsec site-to-site tunnel, so you do an FTP, but you still have to be wary of those remote transfers. So what about insider threat? Because imagine you're doing this from your computer. How many hops in between does it take for you to get to that server at the HQ? Probably maybe a lot of switches, maybe some Wi-Fi involved. So, got to be careful about that. API calls. So when we're running APIs to that back-end API service or front-end or whatever that API service is that we're interacting with, are we protecting that transaction? So cryptography protects data in transit by encrypting communication so that intercepted data cannot be read or modified. So what did we talk about in class a lot? That is like one of the main ways we protect this data in transit when it's like across the web or it's end to end, like a host to like client to server. That's TLS. But other data in transit encryption, like if your email, you have stuff like SMIME. So even if that maybe crosses like a TLS tunnel to get to its destination, at the actual like email itself, we can encrypt that message. We can actually encrypt that email message. Again, for our site-to-site, we have things like IPsec tunnels, and that's Internet Key Exchange version 2 is like the most up-to-date with our advanced cipher suites. And same with TLS as well. Want to have advanced cipher suites. So TLS like 1.3 with ECH and IPsec IPv2. Really, there's no like version of it, but you just want it, the highest level encryption, the best group that you can pick for IPv2. And also a better way, so it's more trusted, is you can have certificate-based authentication with IPsec. Don't think I missed anything. Now, obviously for APIs, when we do like API calls, so let's say, I have my user here. I'm doing an API call to like a backend. Actually, I'm going to do this. Whoop. Database, right? So if this is our API here, and we're making this call, we want to have some kind of encryption on that as well, which, guess what? Could be like TLS. We could add TLS to this. Here, we want to add some like authentication as well to that API. And if we're doing this from like, let's just say a Python script, or wherever we're making that API call from, what do we not want? I'm going to use my red color here. We don't want embedded or baked in secrets. We don't want embedded secrets. That's where the key is just right there in the code, and you're hosting this code somewhere if you're like in any sort of enterprise at all, in GitHub or something, and we don't want that key there. Maybe we want it rotated, and we want what's called, and I'm going to use my green color now because this is like good, secrets management. Somewhere, some key vault, maybe it's a HSM, maybe it's just in software, some key vault that stores those keys that allow us to authenticate like to our APIs, or when we do like some federated services like SAML, OAuth 2.0, OpenID Connect. How do I clear? There we go. Encrypted tunnels, kind of already talked about that. Or SSH, that's a great one that I missed. Like management, when we're managing servers and stuff, we use SSH, which uses asymmetric encryption RSA to make that happen. So I'm not going to spend too much time on that. We use encrypted tunnels. Strong encryption, large bit key lengths. Don't use exploitable cryptography like RC4 stream ciphers, things like that, guys. Don't use MD5 for the integrity of the hashing. Use SHA. Data in use and data during processing. So this is one that doesn't get touched a lot in like previous levels of like cybersecurity. You look at like Security Plus, CYSA, but it is something that we have to worry about being protected. No, it's not the biggest attack surface. You have to usually get access to that device in some sort of way, whether that's like in-hand access or you downloaded, you hit the link, you fell victim to that phishing email. and now there's a virus or malware or whatever. But data in use refers to data that is actively being processed in system memory or by a central processing unit. Traditionally, this has been the most difficult data state to protect because data must be decrypted to be used by the application. So this is going to automatically expose sensitive information. So what we're saying here, where like data in transit, data at rest, was kind of easy, not easy, but it's easy to understand that we encrypt it. We encrypt it, and as long as someone can't decrypt and we protect that key that decrypts it, we're usually in a good spot. We're using strong cipher suites. Unless they're inside, they're an insider threat, they have the key, they're usually not going to get that information at rest or in transit. But with data at use, it's like I'm running Google Chrome. I'm running Canva right now, this application. Well, guess what? That's data in use. And does it look encrypted to you? No. This is plain text. This is human readable. So if there was a virus here, it could be easy to gather that information and look at that data in use. So, but we do have some options. We do have some solutions. So modern cryptographic and hardware-based techniques aim to reduce exposure during processing. This is secure enclaves, trusted execution environments, memory encryption, confidential computing, and then homomorphic encryption, which we talked about, the big thing in the cloud where we keep things encrypted and we can actually process against that homomorphic encryption. Something's not listed here, and I probably will add them, I'm going to type it out, is ASLR. Yes, that stands for address space layout randomization. That's a protection mechanism for protecting against like memory-based attacks, which is essentially, you know, our data in use. And then we have XN/NX bits. And this also protects data in use. And this is for like the CPU, so like CPU-based attacks and threading and things like that. I can't remember, you know, I'll probably just look it up because, yeah, let's just go ahead and look it up. XN bits, is that Intel or AMD? Yeah, there you go. So execute never, similar for AMD's is Intel's. Okay, XN is Intel's, NX is AMD's. Okay, they do the same thing. Okay, where'd my mouse go? Let's see. Okay, secure email. Talked about this, using things like S-MIME to encrypt the email, securing the email server. This used to be a big deal when we had like on-prem Exchange servers. Email systems are inherently insecure by default. So yeah, like, you know, like POP3, like those actual email protocols, like IMAP, they were never secure in the first place. They weren't built with security in mind. So pretty much we just had to add like authentication, integrity, and encryption on top of those, like email messages, communication protocols. So secure email systems typically use encryption to protect message content, hashing to ensure integrity, and digital signatures to authenticate the sender, give it non-repudiation. And we're going to leverage PKI to establish the trust when we add in all this stuff. So common secure email standards include S-MIME and PGP or GPG. Okay. These systems rely on digital certificates and public-private key pairs to protect email communications. And mainly just like it's TLS, right? Like S-MIME, it's TLS. Okay, immutable databases and blockchain. Immutable databases are designed so that once data is written, it cannot be modified, deleted without detection. Cryptography enforces immutability through techniques such as cryptographic hashing, hash chaining, and digital signatures. Blockchain technology is a specialized form of immutable database that uses cryptographic hashes, distributed consensus mechanisms, and digital signatures to maintain a tamper-resistant ledger. So blockchain is kind of built on like distributed computing models that have actually been around a while. That essentially says if all these millions of nodes agree on a cryptographic hash transaction, then it must be secure and authenticated. And really the only attack against that is like called I can't remember, I think it's like a 51% attack, where if you're able to infect 51% of the nodes to disagree with a transaction that is actually authenticated, that's how you can break the blockchain. But that's so, you know, with so many nodes a part of that blockchain now, more than likely not going to happen. Non-repudiation. So this is something I've talked about a lot. This is how you can verify that the sender is who they say they are. That's what the definition of non-repudiation is. And how do we accomplish that? With digital signatures, using an asymmetric or public private key cryptography to create a hash of the message and then encrypt that hash with a private key. And then the receiver uses the public key to decrypt that hash and then sends that same hash algorithm against the original message. And if the hash that it produces is the same as the original hash, we verified integrity and we verified authentication because the sender's public key was able to decrypt that private key. So we're not looking for confidentiality, right? We're looking to decrypt to verify that it is the sender who encrypted that. So the best way to prove that is that sender's private key, which can't be exposed, well, shouldn't be exposed to anyone, was used to encrypt. So guess what? The only thing that should decrypt is that public key. And that is how your digital signatures work. And when we add a digital signature, that gives us non-repudiation to our messages. And then it's critical in legal, financial, and regulatory contexts as well, where you need accountability. Privacy applications. So cryptography plays a central role in protecting personal and sensitive information. Privacy-focused cryptographic techniques aim to minimize data exposure while enabling systems to function effectively. So privacy-enhancing cryptography is especially important in healthcare, finance, analytics, and large-scale data processing environments where sensitive personal information must be protected while still being analyzed or shared. All right, we talked about this a lot. I think in every domain, we probably touched on like some sort of data sovereignty, but legal and regulatory considerations. So, what we're talking about here is, hey, how you apply cryptographic mechanisms, safeguards, the use case sometimes is influenced by your legal and regulatory considerations. So obviously with things like PCI DSS, you're obligated to encrypt things at a certain level or you can't transact against those major credit card networks. HIPAA, personal health information must be protected at a certain level. And obviously in this exam, we don't dive into those exact standards, but it's important that if you become a cybersecurity engineer in any of those industries, you have to go and read the white papers and say, I know I need to apply encryption, but what type and how much? So like with NIST, is something we're aware of. If you want to do things like, classified communications, not using a type 1 encryption, there's a standard for that. It's called Suite B encryption. There's standards for SSH where it has to be like 4096. There's these, STIG, security template, technical implementation guides that set standards for us, and that's our regulatory considerations in the government. Resource considerations. So I notice this a lot, especially if in your junior or mid-level to your career where you haven't figured out that, you have to, on-prem systems, because you can't just have this wide scalability if you're spending so much on cloud, you have to refine it sometimes. You have to consider your resources. You have to consider how much CPU and memory and storage do we have in this server, and if we have enough, is that actually enough? Because we may need more down the road. You have to plan, you have to future-proof things. So if an application's, this is just a wild thing, like maybe we're like Palantir, is 500 gigs and you have an 800 gig drive to run that, is that enough? Because that's just the operating system and the actual application you're going to run. This is an extreme example, but probably not. You probably want to double or triple that because of backups, because of RAID, because of multiple different things. So when we're applying cryptography, we have to keep that in mind. Like, yes, maybe we want the strongest, but is that going to affect our availability? And do we have maybe like an HSM that can help us, or a dedicated crypto appliance to help us with the key management and the additional encryption we may want to apply? Data sanitation and anonymization. So data sanitation ensures that data is permanently destroyed and cannot be recovered. There's multiple ways to do this. If you're doing this, with solid state drives, obviously degaussing is not going to work because that magnetic, it's not a magnet, it's not like a hard drive. Degaussing works for hard drives. This could just be, hey, we don't need to destroy the drives, we just need to delete it. So we do have programs that sanitize for us, and they're supposed to delete all the remnants. But encryption keys. So there are standards for deleting encryption keys depending on your the sector that you work in, your regulatory considerations. We know that our crypto keys that come out monthly, there's a huge chain of custody for it, paperwork, and proper ways to delete it. And even if that you delete it in the key loader, I'm trying to use vague language. If that key loader gets compromised, all those keys are bad, even the ones that were potentially deleted, So Once encryption keys are destroyed, the encrypted data becomes unreadable and considerably effectively erased. So what we're saying here too is like if you encrypted something with this private key, if you destroy that private key, it's supposed to be, we're screwed now, right? We don't know, we can't ever unencrypt it again. Data anonymization removes or obscures identifying information so that individuals cannot be easily identified. Cryptographic techniques used in anonymization include hashing identifiers, tokenization, encryption with controlled access, and pseudonymization. So tokenization, a great example I like to use is like our tap to pays. That's like data anonymization, which it's really a token. It creates a token that gets sent to the bank that correlates to your credit card numbers and account, and then that token gets replaced after every transaction. So if someone does intercept that token, it's not going to be usable again. So that's a form of data anonymization. So we're not sending our actual credit card numbers and CVV across a network. So yes, the tap to pay is actually more secure. Okay, now we're going to go over authentication. So certificate-based authentication uses digital certificates rather than passwords to verify identity. We use a version of this, when we use our common access cards. That has a certificate in it on that little chip, but then we couple that with another factor, something factor, like a PIN. But that is certificate-based authentication at the end of the day. You have a user account in your domains, your DoD domain, whether that be regular NIPRNet or like SoftNet, that gets correlated to that digital certificate that lives on your common access card, and that that correlates to your Active Directory account. So that's certificate-based authentication. This can also be done with like our encryption as well. So like I talked about IPsec, let's say using FlexVPN, you could use a certificate to do the authentication rather than just a password on those IPsec tunnels when you're making those connections to the outside IP. Passwordless authentication. So passwordless authentication aims to eliminate reliance on shared secrets such as passwords. A lot of times this is just with something you have. So this is like, those RSA little things that go on your keychain. Just using that. We don't even have a password involved. That's using multi-factor authentication, an app on your phone, sending a push notification, or like even certificate-based authentication, when it's just a certificate, could be a form of passwordless authentication as well, or it could be something like biometrics. So when we remove passwords, it actually reduces the risk. It actually reduces the attack surface a lot, because now we don't fall victim to some password cracking or brute force attacks. But, it's not always feasible, it's not always possible to do passwordless authentication, but that is technically, by the standards right now, the most secure way to protect identities. All right, software and code integrity and centralized versus decentralized management. So cryptography ensures software integrity by detecting unauthorized changes to code or system files. What kind of cryptography techniques do this? That's going to be hashing and digital signatures. So imagine you signing code on your GitHub repo or whatever repo, and someone downloads it. They can either verify that digital signature by, again, using that public-private key like cryptography, or with just regular hashing, we could send a hash against that entire code base and say, hey, does that match what I downloaded from the website? So we know nothing was altered in between me downloading it and it getting to my computer. Key management determines how cryptographic keys are generated, stored, distributed, rotated, and revoked. And centralized key management systems, keys are controlled and managed from a single authority. Maybe that is like a single HSM that does everything. This simplifies policy enforcement and auditing because you only have to go to one place. But decentralized key management distributes keys across multiple systems or entities. So this is kind of like distributed computing, what we've already talked about. It's kind of like all these decentralized things, authentication, key management, comes from that distributed computing model where there's a bunch of nodes agreeing on something. So this increases resilience and reducing trust concentration, but increasing complexity and administrative overhead, because now maybe you have a bunch of nodes that you have to audit against, apply policy to, and put in protection mechanisms. All right, let's go ahead and do our quiz. I need it not on this one. I need it on my other site. There we go. Okay. Quiz for domain 3.8.1. Is it not there? Okay, that's weird, because I'll reach it this way. Don't know what's up with that. All right. Try to fix this later. Okay, question 1. All right. A company implements a system that records financial transactions in a way that prevents past records from being altered without detection. Each new record is mathematically linked to the previous record, and any modification breaks the integrity of the entire record chain. Which cryptographic concept is primarily responsible for providing this protection? Yeah, this is like that distributed model again, decentralized, but yeah, this is hash chaining. All right, good job, guys. Question 2. An organization wants to eliminate password-based authentication for remote access systems. Users must authenticate in a way that is resistant to phishing attacks and does not rely on shared secrets. The organization also wants to cryptographically verify user identity during authentication. Which solution best meets these requirements? Yeah, it's A, definitely, right? Password-based authentication with password policies, obviously not. We wants to eliminate password-based. Hashing user passwords, no. We don't want a password. One-time passwords delivered via email, no. We want to probably go with C here. Certificate-based authentication using public key cryptography. All right, question 3. An organization stores sensitive customer records in a cloud-based database. The data must remain confidential even if the underlying storage infrastructure is accessed by unauthorized individuals. The organization also wants to ensure minimal performance impact when encrypting large volumes of data. So we want to minimize performance impact. Which cryptographic approach best addresses this requirement? Encrypting database traffic using TLS? No. Encrypting database using symmetric encryption? Probably, because performance. Applying digital signatures? Nothing to do with encryption. Hashing the database files has nothing to do with encryption either. So we're going to go with B. Encrypting the database using symmetric encryption. Awesome. All right, another 100%. Now let's move on. Let's finish up domain 3. Okay, now we're going to finish up domain 3.8.2. Given a scenario, apply the appropriate cryptographic use case and or technique. And now we're going to go over the different techniques. So we're going to go over everything in red here. Okay, so tokenization. This is a data protection technique that replaces sensitive information with a non-sensitive placeholder called a token that's going to correlate to your identity or your account, whatever that may be. The original sensitive data is stored securely in a separate system known as the token vault, while applications and databases only use the token. And again, a great example of this, because it's such a daily use thing, is when you tap to pay, the bank creates that token database that does correlate to your account, and then your account is like separate from that. All right, because tokens are meaningless outside of the tokenization, let me see. Sorry, if an attacker compromises a database, because tokens are meaningless outside of the tokenization systems, tokenization significantly reduces risk. If an attacker comprises a database containing tokens, they gain no usable sensitive information unless they also breach the token vault. This separation greatly limits the impact of data breaches and simplifies its compliance and regulations. Tokenization was commonly used in environments that process highly sensitive data, such as payment systems handling credit card numbers. See, like I said, right? That's a big one. Did I skip? Okay. Code signing. So code signing is what I talked about. Like, let's say we have our source control management in GitHub, or wherever the case may be. We have some sort of source code. We can sign that, we can add a digital signature, we can add a hash, and we want it to become a trusted source. Think of this like when you're going to the Docker like Vault to get like a container image, not the Vault, but just the Docker website, that's a trusted image because it's something that we can verify. We can run a hash against it and make sure. So it works by generating a cryptographic hash to the software and then digitally signing that hash using the software's publisher's private key. And then again, we can use that public key to decrypt it and say, yes, that is from the sender. So when a system installs or executes the software, it verifies the signature using the publisher's public key. If the software has been modified or tampered with, the hash will not match and the signature verification will fail. Cryptographic erase and cryptographic obfuscation. It's always hard for me to pronounce that, obfuscation. All right, anyways. Cryptographic erase is a secure data destruction technique used with encrypted storage systems. Instead of overriding old stored data, the encryption keys protecting the data are destroyed. So, that's like, hey, maybe we have terabytes and terabytes of data that's encrypted using the same key, and maybe we need to just get rid of it. We need to get rid of that data now. We don't need to archive it. We're just going to delete it. Well, the easiest way, probably I would still shred the disk. And, you guys working in the DoD, we know, like, yeah, that's not good enough when we're turning it into DRMO. We need blank data. But what they're saying here is we can just get rid of the private key. And then if no one has access to that private key, there's no way they can decrypt this. That's kind of like the logic behind that. And then cryptographic obfuscation focuses on making data or code difficult to understand rather than unreadable. That could be using like, code names, things like that, getting rid of sensitive data in there. It's commonly used to protect intellectual property or hinder reverse engineering. Maybe coding in a way that's not best practice. I've heard of that a few times. Obviously, that's not very common because every software engineer pretty much learns to code the same way. Okay, digital signatures. I've talked about this a lot, but it provides that non-repudiation. In short, because I kind of described this in the last section, maybe I'll draw it out here. So in short, this is how digital signatures work. Imagine you have a message, you're the sender. And here's your message, you're the sender. So you want to add a digital signature. So let's say your message is hello. What a digital signature is going to do is it's going to apply a hash to that message. That hash is going to create, whatever. Wait, I don't want to use like an actual hashtag. I'll just do an actual hashes. So you're going to apply a hash against that. Maybe it's like SHA-256. And that's going to create your message. Your message digest, okay? So this is your checksum or your message digest. And then what we're going to do is we have like a public and private key pair that's in the GAL, in our global address, in our global enterprise. So this is something you can publish on Outlook, right? If you have that, like we do that, right, in the DoD. What we're going to do is we're going to take that private key and we're going to encrypt that hash. And when we encrypt that hash, that's going to create a whole new, we're going to encrypt it. So it's going to turn that hash into another form of ciphertext. So I'm just going to do 1, 1, 2, 2, 3, 3. And this is our digital signature. Okay? And then we're going to add this digital signature to our original message, which again is not encrypted or anything, so we still have that hello there. So we're going to add that. That's our digital signature. Now when that gets sent to the receiver, I'm going to use a different color now. So here's the receiver. So the receiver gets that message. We see a digital signature on there. I'm just going to put DS, digital signature. What's the first thing that receiver is going to do? It's going to grab that public key and it's going to decrypt this message. If it's able to decrypt, because guess what? The sender used his private key to encrypt. So what's the only thing that can decrypt? That's the public key. So if this decrypts and we get this message digest, ABC123, we just verified authenticity. I'm just going to put authentication essentially. But now that's still a hash. So we verified authenticity by using the public key to decrypt the private key of that digital signature. So we know it came from this sender. And we'll say the sender is Bob. You know, it's always Bob and Alice in the book. So we'll say Bob. Here's Alice. What's the next thing we do? We take that original message now. So we still have that original message. That hello. And we're also going to send it through a hash. Okay? Now we have that original hash here. So once we send that original message, once we receive it through the hashing algorithm again, if we get ABC0123, it's the same as the original one. I'll put this up here, original, OG. Then we verified what? Integrity, that message wasn't changed during transit. So that's exactly how digital signatures work when you apply it to your email. Hopefully that wasn't too much gobbledygook up there on the screen. But that's how it gives us what we call non-repudiation. We know it is from that sender, and we get integrity by verifying the hash hasn't been changed, because that means the original message hasn't been changed if they can match. So what's another thing about that, guys, right? We don't really add salting or any of that key stretching to it because we need to verify the same exact hash, right? Okay, obfuscation, even though we just already talked about it, but we'll talk about it again. Obfuscation is a technique used to intentionally make data or code harder to read, analyze, or reverse engineer. Unlike encryption, obfuscation does not guarantee confidentiality and is often reversible with sufficient effort. You know, it's like you're just reverse engineering essentially. Like, do we have that, you know, that code word list? Move on from there. Okay, serialization. This is the process of converting data structures or objects into a format suitable for storage or transmission. This is what we talked about already, like when we're transacting against a database, going to our back end application, then to our front end, we use a common data serialization format like JSON or like XML. So with those, that's a target. That is an attack vector. That's a vector of attack that increases our attack surface. We have to have JSON going all over the place, especially if we have like a distributed microservice architecture where this is not something that I agree with. It's just something that could happen. We have microservices in the cloud. We have APIs talking to like Azure Functions, talking to a database that may sit in even different regions. Not recommended because that would, you know, latency and things like that. But we want to protect that. So with like JSON, we have JWTs, like JSON Web Tokens, that can offer us authentication. And then, of course, if it's like a REST-based APIs, which is over HTTP, what do we want to do with that? If we're sending JSON over HTTP connections, we want to add that S on there so that it's encrypted. Okay, just a definition of hashing. We've talked about hashing a lot, so again, I'm not going to read the entire thing. Hashing is a one-way cryptographic process that converts data into a fixed-length output known as a hash. Cryptographic hash functions are designed to be irreversible, meaning the original data cannot be reconstructed from the hash. Now, obviously, we know it's not true with all hash algorithms. We want to use advanced hashing, well, not even advanced, strong hashing algorithms like SHA-256, 512, longer the bit key length, the stronger it is. And then do things like key stretching, you know, adding salt, adding randomization to it, the original message when applying that hash, so we don't end up with like collisions, you know, or someone trying to reverse engineer a hash from like a known list of data inputs. Okay, a one-time pad. So one-time pad is an encryption technique that is theoretically unbreakable when implemented correctly. It uses a truly random key that is at least as long as the message is never reused. So, yeah, you know, a one-time pad is like, think about the initialization vector on like a block or stream cipher that begins that cipher, right? And when we do that, we're supposed to never reuse it again. So if someone is doing like a packet capture, you know, of our encrypted data, they may try to recreate something, but the one-time pad, they can't recreate it because that's exactly what it is. So if all requirements are met, the ciphertext reveals no information about the plain text. However, these requirements are extremely difficult to satisfy in practical systems. Essentially, we're saying some, you know, computer scientists at probably like some high-level school proved this in a lab, but, you know, can we sell this to somebody? Probably not, because, you know, there may be a lot of tech debt and a lot of resource computation. All right, symmetric cryptography. So symmetric cryptography uses the same secret for both encryption and decryption. Guys, give me 1 second.
What are you doing?
Honey, go see mom. I'm teaching.
Teaching? Oh my God.
Yeah, honey, I'm teaching right now. Just go see mom. I love you. All right, sorry. That was my, I have a 3.5-year-old and a 2-year-old. So their mom probably fell asleep on the, on the couch or something. So sorry about that. All right. So symmetric cryptography, we talk about this a lot. This uses the same shared or secret key for encryption and decryption. So this is what we want to use for a lot of our bulk encryption, you know, our data at rest, data in transit encryption. But obviously, what's the problem with this? Why do we have to use asymmetric and a secure key algorithm to get to symmetric encryption? Because if I'm using symmetric encryption and I encrypt data and I send it to you, what do you need? You need my key. So how do I get that key exchanged to you securely? And that's where, you know, TLS, asymmetric encryption comes in. Common symmetric algorithms include AES and Cha-Cha-20. Cha-Cha-20, like Salsa-20, a lot of those are stream ciphers that get used a lot, like for TLS and things like that. She went back inside, Amanda. Asymmetric cryptography. This uses, you know, public-private key pairs. We've talked about this a lot. They are mathematically related. And asymmetric cryptography is how we get that secure key exchange to do symmetric encryption. We don't like to use this for bulk encryption. You know, we literally use it for that. We literally use it to get to that symmetric stream cipher encryption. It's used in PKI, though. It's also used for a lot of trust. And asymmetric cryptography can be used a lot in like authentication and non-repudiation use cases, like I showed you in digital signatures. Okay, let me draw this out. I mean, I think it's important. Even though I know it's SecurityX and you probably already know this, but you know, let's just do it. So how asymmetric encryption works, guys, here's Bob. Bob needs to send a message to Alice. And we want to use this for like encryption, right? So Alice has her private key that stays local. She's also going to have, I don't like to use red, but fuck it, they'll both be red. And then she has her public key. That should have been opposite, but it's too late now. And then Bob has the same thing. He has his private key. And then he also has a public key. So remember, these are both mathematically related. So if the public key encrypts, what's the only thing that can decrypt? That is the private key. If the private key encrypts, what's the only thing that can decrypt? That is the public key. So if Bob wants to send a message to Alice, let me shorten up my line width here. He's going to go grab, hold on 1 second. Bob is going to grab Alice's public key and encrypt his message using the receiver's public key. So you know, that's what we call this. You know, this is the sender and this is the receiver. So once I encrypt this message with the receiver's public key, the receiver, you guessed it, receives it. They're going to use their private key to decrypt. Okay, that's asymmetric encryption. When I teach this in like Sec Plus, like it's always like, and I talk it through like that. Usually my students are like, oh, that's what that meant this entire time. Like, yeah, like, you know, it's actually not that difficult. And I don't know what it is about like intro to cyber and classes like that. They try to complicate it sometimes, but that's as simple as it is. You just, whoever that sender, receiver, client, web server is, using an asymmetric cryptography algorithm, something like RSA, we're like, hey, here's a public and private key pair. They're mathematically related. One encrypts, the other decrypts. As simple as that. But when we're doing that, we're sending a message to, you know, our web server or the receiver, whoever we're sending the message to, we use their public key. Because guess what? If anyone intercepts that, they're not going to be able to do shit with it anyways, because they need that receiver's private key, which is stored in a secret place, to decrypt. Okay, and this one was a new one for me. Lightweight cryptography, when I was making this course, I haven't heard of this before. I think what this is saying is that there's just encryption algorithms that probably aren't as secure, that are made for, low threshold, low CPU, and things that maybe not on, a high value target for like attackers. So it's like, hey, it's better than nothing. But lightweight cryptography is designed for devices with limited processing power, memory, and energy availability. Examples of devices that would use this is IoT devices, embedded systems, and smart sensors. 1 second here, sorry. So, lightweight cryptography is increasingly important as more devices become network connected. But again, it's just for things with low power consumption, low CPU, whatever the case may be. All right, let's do our quiz. All right, let me bring it up here. Let me get it prepped. I don't know why it's like acting weird, those links. When you do these quizzes, guys, if you're doing them with me, come here to quizzes. For some reason on the lesson page, it's like all messed up. Okay. All right, let's do this. Question 1 of our domain.3.8.2 quiz. An organization distributes software updates to thousands of endpoints across multiple locations. The security team needs to ensure that updates have not been altered and that they originate from the legitimate software vendor. Which cryptographic technique should be applied? Let me bring up that Zoom chat. Let's see what y'all are saying. Remember, altered and originate. That's okay, Masood, because guess what? On the exam, you can flag questions, so you would have went back and you'd be good. Yeah, C is just integrity, so that fits the altered. But the key one there is originate from the legitimate software vendor. So that's going to be, we need authentication, or what we call non-repudiation, right? So the only thing on here that gives us both integrity and authenticity and non-repudiation and all those fancy words is digital signatures. Question 2. A healthcare organization wants to reduce the impact of a potential data breach involving patient records. Applications must still be able to reference patient identifiers, but storing actual patient data in multiple systems is considered too risky. Which cryptographic technique best meets this requirement? Okay, so impact of potential data breach, not that we're stopping the data breach. We're saying if we do. So like, let's say, not that we're accepting it, but if we do get data breach, we want to minimize the impact when it comes to our patient records. But, we need some identifiers for it. And we can't store it in different data systems where we may have to encrypt, okay? So, yeah, I agree with you guys. It's probably going to be D here, tokenization. It's not A because we can't use encryption. B verifies integrity. And if we hashed all of our patient records, we couldn't, and we just, we didn't have, it still leaves it in plain text. It's not like, that's not encryption. It's still available. It just means that we verify the integrity, right? But yeah, this is a good example of like credit card transactions. Yep. Tokenization. Yeah, that's always an example I like to use too, because there's so many people actually, like, there's great YouTubers that go over exactly how that process is and how they say that really is the best way to do it. Because even if, I don't know if you guys have seen like those skimming cards, like those gas station attendants that skim cards, and they capture that transaction, they get credit card numbers. With Apple Pay, you can't do that because it's literally just a token. So to get the credit card information off an Apple Pay or Google Pay transaction, you'd have to hack the bank, right? And that's, never say never, but probably not gonna happen. Yeah, but then, so I don't know if this ever happens to you guys, but every single time I go to Publix, Sprouts, and I use Apple Pay, You know, groceries today, if you want to eat any sort of healthy, is like fucking expensive. And if it's like every single time, if it's over $300 for me, USA denies it. But then if I use my card, like my actual card, it accepts it. And I've asked them like why. Like this is the same POS systems I've used everywhere else. Why is it just the grocery store? They never know. But I'm sure there's some extra contextual awareness the banks do with that Apple Pay, and I don't know why, don't know what reason they have, but I'm sure there is. It's so annoying. It happens every single time. It's embarrassing. I got my kids in the car and they're like, yeah, it's declined, big dog. And sometimes I don't bring my fucking credit card with me because I just... Anyways, sorry, moving on. Okay, a company deploys thousands of Internet of Things devices with limited CPU power, memory, and battery life. The devices must still use cryptographic protections to secure communications. Which cryptographic approach is the most appropriate for this environment? Okay, yeah, this one, we just went over it in the slide. If it's an IoT device, something with low CPU, low compute resource, we're going to go with lightweight cryptography. So that's going to be C. All right, awesome. Another 100%. Let's go, people. All righty. I've yapped for a long time. So let's go ahead and take our first break, guys. And then when we come back, I want to get all the way through domain 4.2.1 because then we only have 4 slides after that. So we can, do a good job on our final day. Okay, guys, let's go ahead and go over domain 4 now. Before we start, let's actually just take a look at domain 4. Let's go to our Google Drive. Oh. Exam objectives, there we go. Oh yeah, let me just download it real quick. I know it's on my, it's been downloaded like 5 times on my computer, but okay. Yeah, so it's domain 4 security operations. It's the, third, I guess you could say third smallest or third largest domain. Let's just take a look at it here. We got through domain 3, that's the big boy. So we just got 4 subdomains to go over in domain 4. Yeah, the slides are a little longer sometimes in some of these because, it's just a lot to go over again. But again, we've talked about so much of this already, so we can get through some of it quick. But in domain 4.1, it's all about monitoring and response activities. So we'll go over SIME, aggregating data, alerting, data sources, again. Okay, just make sure my mic, everything is good here. Let's do it. Okay, so now we're going to go over domain 4.1.1, given a scenario, analyze data to enable monitoring and response activities. In this section, we're going to go over SIME, aggregate data analysis, baselines, reporting, and metrics. So here is all the exam objectives we're going to cover in the domain 4.1 slide deck. And in the red is what we're going to cover in these slides. So first, let's again talk about security information and event management. So SIME, SIM, depending who you talk to, they pronounce it different ways. I used to call it SIEM, and like cybersecurity guys would be like, what are you talking about? Like SIM, SIME, whatever. Security event information and event management system, commonly called as SIME, is the foundation of modern security monitoring and incident response. And that's very true. If you go into a SOC and they don't have some sort of data aggregation, log collecting, dashboard system that touches in process data and transit data and then logs and historics, probably not a real SOC. And I don't mean that to be disparaging. It's just, it just covers so many of our blue teaming activities. It's rolled up into a single application, appliance, server that it's kind of hard not to have that skill on your resume if you're looking to be like a cyber analyst, 1, 2, 3, engineer, administrator, whatever the case may be. In most organizations, security-related data is generated by many different systems. I'm not going to, we can talk about all of it. It's network devices, it's endpoints, and it's servers, and it's cloud resources now, and then also user IDs or objects. It does collect logs, it does aggregate data, but SIME is a way for us to index and start to centralize not only logs, but our capabilities in monitoring and alerting and advanced protection mechanisms. SIME also introduces AI-enabled learning and remediation. From a response perspective, the SIME acts as a primary investigation platform during a security incident as well. So in the event we are exploited, that may be the first place that we start to dig deep to find out where that exploit is, and then we may move to that device that, of course, was exploited. Okay, so now we're going to go over different things we can do in SIME, and this is just going to be the common things that are possible. So it's going to be event parsing. So event parsing is the process of converting raw log messages into structured, meaningful data that a SIME can analyze. So what we're saying here is, we have so much data that we have to look at in a SIME system that we need some way to narrow down the noise to actually look at what we need to as a cybersecurity analyst or during our blue teaming efforts. So security tools generate logs as lines of text that may include timestamps, IP addresses, usernames, error codes, and descriptive messages. And without that way to index and do the parsing on all those events, we're just going to be doing log dives into an ocean instead of what should be, a nice, easy way for us to interpret things. So a good example on here. A failed login log may contain a message stating that a specific user failed to authenticate from a particular IP address at a certain time. Through parsing, the SIME separates this information into discrete fields such as the event type. So what kind of, was it account lockout? source address, destination system, timestamp, and even advanced things like geographic location and things like that. So accurate parsing is essential for us actually utilizing the SIME in a logical way to actually help with our blue teaming efforts and in our SOC actual good monitoring. Event duplication. So event duplication occurs when the same activity is recorded multiple times by different systems. So think about this. Think of a firewall in an active state. Now, or a WLC, it really doesn't matter. I'll go with a WLC example, a wireless LAN controller. Imagine it's in an active state where they're sharing those CAP-WAP tunnels. Let's say everything that a WLC1 does, WLC2 does. That could include log messages and log generation. So guess what? We may have some event duplication because the way a SIME works is we may go, hey, we're not seeing that as one logical high availability pair. We see it as a single IP address of a WLC1, WLC2, even if, yes, logically it's one device, in our logs it sees it as maybe two devices. So we need to manage that properly. So there's a lot of different ways. Example up here, in a typical enterprise environment, a single action such as a login attempt may be logged by the endpoint, an authentication server, a network device, and a centralized identity platform. And that's true too. And those logs may arrive in a bunch of different formats because the Windows event logs, the Cisco iOS switch, and maybe the Cisco Identity Service Engine may all log that in a different way, with maybe some doing the timestamp first or last. There's so many different things, and that all gets aggregated into our SIME. So when duplication is not managed properly, it can overwhelm analysts and inflate alert counts. And again, we can't cut through the noise to see maybe a larger attack pattern or advanced persistent threats that may be hiding on our system or active exfiltration, wherever the case may be. So SIME platforms do have ways to address this through deduplication and certain aggregation techniques. You can start to build your SIMEs in a way that works for your SOC. Maybe you group every network log into one thing, endpoint logs into one thing. You can get real granular with the logs on the endpoints. In our accounting VLAN on Windows 11 machines, it goes into this little, it aggregates to the SIME, but it goes into this little container here, and we build a dashboard on that. There's so many different ways we can achieve this. Non-reporting devices. So non-reporting devices are systems that expected to send logs to the SIME, but they failed to do so. There's so many reasons this could happen. If we're using some sort of authentication for our SIME to even get the logs, if that authentication fails, okay, so that could be a reason. It could be that those credentials are expired. It could be some sort of network connectivity that's being blocked. So maybe we're really hardening switches and distribution switches, or even in our cloud we're really hardening, and maybe some ports are blocked or something that the SIME system uses. It just could be anything. It's typically misconfiguration of either the endpoint or our SIME. So from a security perspective, missing data is often just as concerning as suspicious data. I actually have a real-world story about this where an administrator downloaded software that was not on the allowed list, and the software was, guess what? Key purpose was to delete logs, was to black out events in Windows machines. And then that software was also downloaded. The EULA was from Russia. So there could be a malicious reason as well. We're in a cybersecurity course here, so from a security perspective, if we're missing data from a single device, it is worth investigating to see if it's something malicious or just a misconfiguration. Retention. So retention refers to how long log data is stored and accessible within the SIME. So these are just our retention policies. And really this depends on how robust your enterprise is. Because we may have, again, logs being aggregated and it's just noise. It's not really something that we need to track. It could just be, like in the Cisco networking world, there's syslog messages that are just notifications. They're just alerts that generate. They have no really meaning. And there's these critical levels. So if we're getting these, level 5 and above syslog levels on a Cisco device and we're sending that to a Kiwi server, we maybe don't want to store that a long time. That may be a daily thing. That maybe we don't even store it at all. Our SIME system's the same way. We don't want too much clutter in there. And then this also is off your organizational policy of just data retention, period. If we consider our SIME a sensitive information, whatever the case may be, we may want to keep those logs a long time, right? It's just organizational policy. So security professionals must balance cost, performance, and investigative value when defining retention policies. And it's not always just a resource decision, not always just a storage decision. Like just keep adding more petabytes and petabytes. It's fine. At some point we have to acknowledge that we're running a business with additional costs, and we don't want to keep increasing the costs on our business. Okay, we talked about this before. Event, false positive, and false negatives. Just go over them in a sign perspective. It's the same way in any alerting or logging system. So a false positive is when we say something's malicious and it's not. And then a false negative is when we don't detect that malicious activity. Both we want to fine tune, and obviously a false negative is worse for us. We want to make sure our monitoring is at least accurate. And I always say it's better to have a little noise than miss something. But again, this all depends on your organizational policies. Aggregate data analysis. So aggregate data analysis focuses on examining security data across multiple systems, users, and time periods rather than viewing events in isolation. So individual log entries rarely provide enough context to determine whether activity is malicious. This approach allows security teams to move beyond reactive alert handling and more towards a proactive threat detection. Okay, correlation. So this is just going over really like these next slides is like, okay, now how do we determine, a malicious threat or a malicious activity? How do we correlate it to what's going on? And how do we start to build like a map, a reverse order of events, and how we got to maybe an event that is critical or that is malicious in nature? So correlation is the process of linking related events from different data sources to identify meaningful activity. This could be like identifying lateral movement, like, okay, they're jumping between these VLANs to these types of systems. Is there some sort of pattern there? And traditionally, we'd have to do this one, device at a time before that central log aggregation, but now we can do it from a single place, which is a sign. So for example, correlation may link a phishing email, a suspicious web request, a new process execution on an endpoint, and an outbound network connection to a no malicious server, like a command and control event, a bot event, or data exfiltration. Audit log reduction. So audit log reduction involves filtering and summarizing log data to reduce noise and improve usability. In large environments, the majority of log entries represent routine and expected activity, such as successful logins, scheduled tasks, and normal system operations. Reduction techniques include aggregating repeated events, filtering out known benign activity, and summarizing logs over time intervals. So imagine if you're getting the same message like, NTP authenticated for like 24 hours, and there's no difference in that. Do we need every single log entry saying it just authenticated? No, you could just summarize that to say this day NTP authenticated with no failures, right? That's just a small example of what it means by reducing some of our logs. Okay, and this kind of goes into alerting, like prioritization. So this is, again, up to your organizational policy, how management looks at cyber, how we prioritize SEVs or outages or cybersecurity events. That's all based on your policies, your compliance, your sector, the frameworks you use, the regulations you have to abide by, your data sovereignty. What we decide is the priority as far as alerting, remediation, and detective activities. Trends. So trend analysis examines how activity changes over time rather than focusing on individual events. So some threats are designed to avoid detection by operating slowly and staying below alert thresholds. So trend analysis can reveal gradual increases in suspicious activity that would otherwise go unnoticed. Behavior baseline analytics. I've talked about this a lot. With AI, large learning machine models, we can start to create these baselines of behavior over time, and then we can apply those baselines to when behavior deviates. We can think of that as suspicious behavior and send out an alert based on that, deviated behavior or suspicious behavior. Network behavior baseline. So now we're just getting into the different baselines. So there's the network. This is just going over kind of like the different planes in an enterprise of which we as cyber professionals learn to protect and monitor. So network behavior, that's normal traffic patterns. What ports, what applications are we typically using, and what websites are we typically going to over the network? What's our typical bandwidth usage? We can start to build that baseline and then start to correlate, anomalous events to that baseline. Systems behavior baselines. So systems behavior baselines define normal operation for servers and endpoints. This includes expected processes, resource usage, file access patterns, and administrative activity. And again, something that we could look at is like normal CPU usage for a day. things like that, like resource consumption. If it changes drastically at certain times of the day, it's like, maybe we need to look at that. Maybe we have an infected computer, an exploited device. User behavior baselines. This focuses on how users normally interact with systems and data. This is logging, what they're normally accessing, whether that be through a network connection or on the system itself. We can also create that user baseline that says, hey, this employee is assigned to this computer, and we notice this is usually their day-to-day activity. Applications and services behavior. So again, if we have an application that's hosting a backend API, a front-end API that's public, maybe we see API usage at 1,000 authenticated sessions a day, and all of a sudden we see that spike, and then it goes down. And then we see the conditions or errors on applications that we don't normally see. And we say, hey, well, this was the same version as yesterday. We went through a change management board, nothing changed this application, and now we're seeing these weird errors, That could be suspicious. So we want to take baselines of our applications and services as well. Okay, reporting and metrics. So reporting and metrics translate security data and analysis into information that can be understood and acted upon by different audiences. So what we're saying here is that we don't just serve our own internal SOC team, we also serve a wider enterprise where we may have to report things to management, to our other departments that work in IT, and we want to build this reporting and metrics in a readable, digestible way where people can understand the impact right away. And this helps us support our decision making. So visualization. So the SIEM, it's real easy. The point of a SIEM was to do this aggregation and then create dashboards that we can monitor, and it has numerical values, and we have quantitative and qualitative metrics within the SIEM itself, and we can bring up our SIEM dashboards even in a meeting to say, hey, look, here's what's happening right now to management. So we have different ways to visualize things. Timelines are important when it comes to incident response. We can have graphs, charts, use things like Grafana. But the SIEM system itself will have these visualization techniques we can use inherently. And it usually starts with dashboards. And those dashboards, again, could be graphs, could be charts, could be just numerical values. Like we have 100 computers that are vulnerable to this CVE. Now, out of those 100, we have remediated 60 or patch 60. We still have 40 left. Dashboards like that could be something easy for us. Okay, yeah, dashboards. So different stakeholders require different dashboards. SIEM also does like FinOps, like financial operations. So we can build dashboards from Splunk that look and track our spending and our usage maybe in a cloud environment. Okay, let's go ahead and do our quiz now. First quiz is domain 4. Why are these quizzes not showing up in some of these? I gotta go fix that. Anyways. There we go. All right. So question 1. An organization uses a SIEM to monitor authentication. Let me bring up your guys' chat. Hold on. An organization uses a SIEM to monitor authentication activity across its environments. Security analysts noticed that a single failed login attempt is generating multiple alerts from different systems, making it difficult to assess the true scope of the activity. Which SIEM concept is most directly responsible for addressing this issue? Single failed login attempts generating multiple alerts from different systems. Okay, yeah, so kind of exactly what we talked about in the slides. Yeah, that's going to be event duplication. That is correct, guys. B. Okay, question 2. A security team is investigating a suspected breach but discovers that several critical servers stopped sending logs to the SIEM days before the incident was detected. No alerts were generated during that time period. What is the most significant security risk associated with this situation? Okay. Breach. Servers didn't send logs to the SIEM days before the incident, so someone went in there and maliciously affected it. So it could be a non-reporting device. Reduce log intention, increase false positives. No. Yeah, we're going to go with C here. Loss of visibility due to non-reporting devices. Awesome. Question 3. A SIEM detects that a user account has logged in successfully using valid credentials. No authentication rules are violated, but the user accesses unfamiliar systems and performs actions outside of their normal job role. Deviations from the baseline. Which monitoring approach is most effective for identifying this type of threat? So it's a user. We are analyzing his or her daily routine, and guess what? They deviate. So this is going to be user behavior baselines and analytics. Awesome. Good job, guys. 100%. All right, let's go ahead and move on to domain 4.1.2. What's UEBA, Masood? Is that user something behavior analytics? Endpoint or something? The E? All right, guys. Domain 4. Okay, yeah. I wonder if that acronym's on like SecurityX. All right, domain 4.1.2. Given a scenario, analyze data to enable monitoring and response activities, diverse data source and alerting. Entity. Okay, yeah. I've heard of that before. Sorry, diverse data sources, alerting. Okay, so in the red is going to be the objectives that we go over. Incorporating diverse data sources. So what are we incorporating into our ability to enable monitoring and response activities? And then alerting. How are we building alerts? What are our prioritization factors? And kind of diving into more what I've been talking about when creating our alerts. Okay, third-party reports and logs. So what is this? Obviously, in an enterprise, we're going to have a diverse ecosystem if we're in a large enterprise of multiple different vendors that we could be working with that maybe have us in, some sort of like email system that sends us email reports, logs, whatever the case may be. So third-party reports and logs originate from vendors, partners, or service providers that support organizational operations. These may include cloud service providers. We don't need to go to all the different providers. Just know that we can start monitoring and looking at the reports that come from our vendors. That's something that we should be looking at, even if we're doing it ourselves through some sort of OSINT. And then, third-party logs as well go over like authentication attempts, APIs, transaction records, audit trails. And what this happens to me a lot, actually. Like in my cloud device, like I told you guys, my CCNA labs that I do are EVE-NG and Google Cloud Platform. And when I'm using like SecurityX or PuTTY to access that EVE-NG environment to configure the router switches in that lab emulation for those Cisco iOS devices, it's Telnet. I actually use Telnet, and I have to source my Telnet and block my, source the IP address of my Telnet. Anyways, every time I use those labs, I get an email from Google Cloud that's like, we see that this like insecure, what is it? I wish I could find the email. Application is running or something like that. This could be indicative of a botnet. Please check out your VMs. And it kind of goes to show like, they monitor everything you're doing in the cloud, and they can decide whether or not they think it's suspicious or not. But every time they just send it to me, and they're just like, nothing happens after. I stopped replying because I used to reply like, hey, this is normal usage for me. I'm fine. These servers are not persistent. They get deleted after we're done with them. Things like that. But could be useful, right? So you should monitor that. Like a cybersecurity professional, you should be getting those emails. You should be on that email list. So if you're not in the email list for the cloud provider you're using in your enterprise, go talk to the cloud engineers or your platform engineers or whoever, management, and say, hey, I want to get some of these reports, Threat intelligence feeds. So threat intelligence feeds provide information about known threats observed across the wider security community. These feeds may include malicious IP addresses, domains, file hashes, malware signatures. So this is just us looking at, it's OSINT again. It's like, hey, what is out there? What can I ingest on a daily basis? Maybe it's like actually ingesting it to your firewall, to your SIEM system, or just me as a cybersecurity professional. So in operational environments, threat intelligence is used to enrich internal data rather than replace it. So for example, if an endpoint attempts to contact an external IP address, that activity becomes significantly more concerning if the IP appears in multiple threat intelligence feeds. So that's something we may want to be tracking, right? To like detect command and control or like botnet systems. I mean, we talked about this, I think, every domain as well. Every like domain 1, 2, 3, and 4, vulnerability scans. Vulnerability scans can help us in our reporting and monitoring as well because it lets us know what CVEs are out there and maybe what open ports are out there. And depending how we configure this vulnerability scan and how often we do vulnerability scans, it can really help us keep a proactive, slash little reactive approach to figuring out what we need to patch and what highs and lows and medium vulnerabilities are out there on our systems. This is something we deal with every week. Our cyber team does Nessus scans every week using ACAS, that Tenable service, and they let the network team know if any of our devices came up as a high on there. Common vulnerabilities and exposures, or CVEs, provide standardized identifiers for publicly disclosed vulnerabilities. Let's take a look. Let's take a look at some CVEs. We don't need to stay on the slides. Let's look at this one. Required CVE record information. This was published 2025-11-20. So, look at that. That's a big one, right? And then we don't go over it in SecurityX, but I do it in my CYSA class where we go over what this string means right here. Like if it was accessed via the network, right? That's like the N. Anyways. But, yeah, here's this CVE. Malicious code is discovered in the upstream tarballs of XZ, so like, compression, zip files in RHEL. Through a series of complex obfuscation, the Libisma build process extracts a pre-built object file from a disguised test file existing in the source code, which is then used to modify specific functions. Does it say how to fix it? I don't think CVEs actually say like remediation. No, they do. Because we've looked at these CVEs. Let's see. Common weakness enumeration. This just goes over embedded malicious code. Let's look at this. CVE fix. $10. Yeah, more than likely this is just going to be like an update though to fix this. Like on the RHEL or whatever, like the software that Tarball XZ records. Anyways, you guys hopefully get the point. You get the point. This is how these CVEs can be useful. We've used these a lot. Like we had one come out for our ASA firewalls that was like, if this is internet facing, you need to remediate immediately because there is like persistence that could live on that ASA and things like that, Okay, bounty programs. So a bug bounty program is vendors that say, hey, if you hack or break my system, I will pay you. That's it. It's a great way to see how, exploitable your systems are in an environment. That's a bug bounty program. DLP data. So data loss prevention systems monitor the movement and handling of sensitive information within and outside the organization. So this is just saying, hey, whatever we classified to be not exfiltrated, that's our DLP data. And we can use DLP data to highlight risky behavior involving sensitive data. So think of like we classify GDPR data and we see that moving across our network or to a destination IP that from a threat intelligence feed, we see that's part of like a blacklisted domain. Well, what do we probably have here? Some malicious data exfiltration. This could include users uploading files to unauthorized cloud services. So like shadow IT. This could help us detect some shadow IT in our DLP data and systems. And when I say DLP systems, remember, this could be a plugin in your firewall, your SIEM. This data loss prevention isn't like a hardware appliance that I sit on my network and now it goes out and does data loss prevention. It's something we have to configure in our security appliances that sit in line, sit in our enterprise environment. Endpoint logs. So endpoint logs provide detailed visibility into activity occurring on individual devices such as workstations and servers. That's why they're called endpoint logs. So these logs kind of capture, if we're worried about our endpoint being exploited, we know someone fell victim to a phishing email. This is the source of truth for what happened or what got downloaded or what things may be happening. And these endpoint logs could be, part of our XDR or EDR, so we may be able to leverage software applications that we're managing from a centralized place. So from a response standpoint, endpoint logs help determine the scope and impact of an incident. And again, that's something we aggregate in our SIEM systems. Infrastructure device logs. So infrastructure logs originate from network devices such as firewalls, routers, switches, and VPN gateways. This is our transport. So our network devices also have logs. Typically, we see this in like syslogs. Maybe VPN gateways may have something a little bit different, but these are our syslogs that we also want to analyze and aggregate into our SIEM and centralized logging systems. So this captures traffic flows, authentication onto the network, like if we're doing network access control, connection attempts. It helps us, like, with this kind of stuff, lateral movement, command and control communication, especially CNC, command and control communication on our botnets has gotten like more sophisticated where now hackers are, hiding it within TLS, that end-to-end encryption. If we're not doing like TLS inspection, which encrypts, decrypts, at the firewall or wherever, we could miss that. Or they hide it in DNS, tunneling through DNS where we see just UDP port 53 to DNS and we're like, oh, like that may not be suspicious, and our automated monitoring and logging systems and alerting systems may not look at that as suspicious either. And then application logs. So this is, our actual maybe web applications or just the services that we use in our enterprise, Active Directory domain services. Technically, that's an application. When you like deploy DHCP service on a Windows server, that's an application. It's a server, it's an endpoint as well, but those may generate logs. So when we're thinking about application logs, we're thinking of like authentication errors. Maybe we're getting messages from our IDP that we're using a centralized IDP that we're getting authentication errors, API usage, things like that. So during monitoring, application logs help detect attacks such as credential stuffing, injection attacks, and abuse of application features. Cloud security, posture management data. So cloud security posture management data focuses on configuration and compliance within cloud environments. So again, everything we talk about on-prem does get translated to the cloud, and it's always a little different. Why? I kind of said this all week. That's because there's service provider responsibilities and there's customer responsibilities. So there is going to be CSPM tools to identify misconfigurations such as exposed storage, things wide open on the cloud, with public IPs, excessive permissions, or insecure network settings, which is like I say, it's a common thing. We have good cloud engineers now, but like when a system admin or network engineer doesn't really have the experience, they go into the cloud, they may not always understand how like, I'm speaking from Azure, how VNets or like VPCs work, or how we apply like ACLs to that VNet or to a region or to a zone, not a region, but like a zone. So in monitoring operations, CSPM data highlights risky configurations that can increase the likelihood of compromise. Okay, alerting. So we talk about alerting a lot. This is, hey, we have a SIEM and we have a monitoring system. Maybe it's an IDS, we have something. And we need to start categorizing how we alert. So are we going to alert via email, via text message, via phone call? And is this going to go to the entire SOC team? Is this going to go to just the on-call cybersecurity engineer? And how do we categorize the severity of when we should alert? So configuring alerting is just as important as configuring the rule sets and the automatic run books and playbooks that remediate malicious events, because we can't just AI everything, not yet. We still need that cybersecurity engineers to know what is critical and what is not critical. And then we also need to fine tune our false positives, our false negatives, and get to the true positives, or get to, maybe there's nothing. So alerting. Prioritization factors. So criticality refers to how essential an asset is to a business operation. So this is a great example. So remember, a lot of times we forget that we're working for a business, right? So we have to worry about profit. And now, even if you're a cybersecurity engineer, a nerd that sits in a closet somewhere that's like, no, I'm doing my blue teaming and I'm, simulating red team attacks, we have to realize that we're enabling business operations. So a CVE that is like a 5 CVSS score, if that attacks e-commerce servers that generate profitability for the company, guess what? Not that we monitor that more than other devices, because other devices could be how we exploit lateral movement to those critical servers, but that may be more important to our SOC analysts. And every organization is like this. We have critical services and servers that enable the enterprise, that enable business operations, that enable profitability, that may require more priority. And then beyond just looking at the systems, not every vulnerability is created equal. Some things may not matter. Like if you're running like a closed off air gap network, is a CVE that has a score of 7 the same as a public facing web server that has a CVS score of 7? It's just not the same. So it's important, right? So malware alerts. This indicates the detection or suspected presence of malicious software. One second, guys. These alerts vary widely in severity depending on whether malware executed successfully, was blocked, or spread laterally. So again, we're not just leaving like systems wide open nowadays. We're going to have EDR, XDR, anti-malware, antivirus, things like this. So we may get an alert saying, hey, malware was detected but stopped, or remediated or contained. So monitoring malware alerts is very important. This could be considered one of the most critical things we do because this is exploits, right? This is how we get exploited. Vulnerability alerts. So vulnerability alerts identify weaknesses that could be exploited but do not necessarily indicate active attacks. This is like I can look at this as vulnerability scans, and it's like, whoa, we have a high, what we consider high here. It's a CVSS score of 7.5, but nothing's happened yet, right? So that's vulnerability alerts. And what you do, what you do with those vulnerability alerts is, again, kind of like up to your organization and the organizational policy that you have, where it says, oh, if we got a high, we need to remediate as quick as possible, do your change management, put together your test plan, and figure out if this is going to break the network or not. And if, we need to get this done within a week because I have a low risk appetite. I don't want any risk in my environment. Oh, okay, quiz time. Let's do it. Let me bring it on this screen. Yes. Hold on, guys. Okay. Domain.4.1.2. Okay, this is a quick. I definitely got a bug going on with some of my lessons because like the quizzes are there, but then that button isn't there on some of them. I'll figure that out. Well, my software developer engineer will figure that out, not me. All right, question 1. Remember, this is the domain 4.1.2 quiz. A vulnerability scan identifies a critical remote code execution vulnerability on an internal application server. No active exploitation is detected, and existing firewall rules limit access to the system. Which additional information would be most important for determining whether immediate response actions are required? Okay, critical remote code execution. I think, didn't we just look at that? Like, wasn't this remote? No, embedded malicious code. All right, sorry, moving on. No active exploitation is detected, and existing firewall rules limit access to the system. Which additional information would be most important for determining whether immediate response actions are required? I don't really like this one. I don't think it's going to be application because it's on a server, right? No, application. Wait, yeah, application server. I'm thinking, sorry. I don't want to just like dead air. Which additional information would be most important for determining whether immediate response actions are required? Immediate response actions are required. Application error logs, endpoint antivirus logs, DLP policy violations. Let's see here. Okay. I think it's going to be the CVE exploitation status. Let's see. Let's read this explanation. Okay. Vulnerability scans identify weaknesses, but they do not indicate whether those weaknesses are being actively exploited. To determine urgency, analysts must understand how likely exploitation is in real-world conditions. Maybe the error logs won't show it being exploited. Sometimes it's like not that it's a 0-day, but I don't know, maybe we need to read the CVE exploitation status to see even what error logs show up. Provides insight into whether exploit code is publicly available and whether attackers are actively using the vulnerability. Okay. If a vulnerability is known to be actively exploited, even systems with some protective controls may require immediate action. Endpoint antivirus logs and application errors may show signs of compromise, but in this scenario, no exploitation has been observed. All right, okay. I don't really know if I like that one. It seems a little confusing to me. Okay, moving on. Question 2. An organization receives hundreds of alerts indicating failed authentication attempts across multiple systems. Most attempts originate from internal IP addresses, and no successful logins are recorded. Analysts are concerned about alert fatigue, but do not want to miss a real attack. Which factor should most strongly influence how these alerts are prioritized? Alert frequency, no. That's not prioritizing, that's just how often. Residual risk? Residual risk is only when we apply a patch or an update, or we apply risk remediation. So we're is there anything residual? And data classification is really only there for DLP and mandatory access control. So I think the only answer we really have here that makes sense is asset type. Yeah, when a large number of alerts occur, prioritization becomes critical. The most important consideration in this scenario is the type of assets being targeted. So yeah, we need to prioritize. Question 3. A security analyst receives an alert indicating outbound traffic from internal workstation to an unfamiliar external IP address. Endpoint logs show a new process executing shortly before the connection attempt, but the traffic volume is small and no data exfiltration is immediately evident. Which additional data source would be most useful for determining whether this activity represents a real security threat? Indicating outbound traffic from an internal workstation to unfamiliar external IP address. We need to figure out if that's bad, essentially, this external IP address. They're saying we don't know if there's data exfiltration happening. So we need to figure out that external IP, essentially. Yeah, we need to figure out this. So I'm going to go with D. I think you guys are right. Threat intelligence feeds. Hell yeah. A, let's go. Another 100%. Yeah, let's finish up domain 4.2.1 and then we'll take our next break. Vulnerabilities and attacks. Okay. See, this one, yeah, this slide is I could spend a week just talking about these types of attacks, but it's okay. It's CompTIA. I got to remind myself. It's not always going to be the most, whatever. On the keyboard type of cert. All right. So now we're going to go over domain 4.2.1. Given a scenario, analyze vulnerabilities and attacks and recommend solutions to reduce the attack surface. So again, we're going to go over vulnerabilities and attacks. So here is all the objectives in this domain. And in red is what we're going to go over. Okay, so starting off, we're going to go over injection vulnerabilities or injection attacks. So injection vulnerabilities occur when untrusted input is interpreted by a system as executable instructions rather than as data. So think LDAP injection, SQL injection, cross-site scripting, things like that. SQL injection is always the one that's talked about the most, but we have different databases now. We don't just have SQL. We have MongoDB, NoSQL databases, whatever, things like that. So the most common example of SQL injection where attackers manipulate database queries by inserting malicious SQL syntax into input fields such as login forms or search boxes. It's user input. We're requesting user input on the front end of our website, and they put in something malicious. So how do we prevent this? What's our remediation? It's going to be input validation and parameterized queries. Now, parameterized queries is a fancy word that we use in these cybersecurity certs, but all parameterized queries really are, guys, is like a drop-down menu or, radio buttons that say, give you options. You know what I mean? So that's really all parameterized queries are. So don't get so wrapped up in that, wondering what that is, or that's some fancy coding, it's just that. Cross-site scripting. So cross-site scripting vulnerabilities allow attackers to inject malicious scripts into web pages that are then executed by a victim's browser. So unlike injection attacks that target backend systems, cross-site scripting attacks exploit the trust relationship between users and web application. Yeah, so prior I just said injection attacks like cross-site scripting. I guess I misspoke, but really both attacks deal with user input fields. Cross-site scripting attacks used to be big in forums and chat rooms and stuff like that. It still requires some sort of input field into that web application. So, but that just makes sense. So, cross-site scripting attacks commonly steal session cookies, capture keystrokes, manipulate page content, or perform unauthorized actions on behalf of users. There's multiple types of cross-site scripting attacks. So, stored cross-site scripting occurs when malicious scripts are permanently saved. Reflected cross-site scripting occurs when scripts are immediately echoed back to users. And DOM or DOM-based cross-site scripting occurs when client-side JavaScript improperly handles input. That one's more kind of like the injection attack one. So, mitigating. So, proper output encoding ensures that input is rendered as text rather than executable code. So, again, it's just more input validation is really what we're saying there. We have additional defenses in the actual HTTP headers, like content security policy headers that are actually in that HTTP flow to kind of prevent this from happening, a cross-site scripting attack. Unsafe memory utilization. So unsafe memory utilization occurs when software improperly allocates, assesses, or manages memory. Now again, this is going to be like a system-based attack, like actually attacking your memory. So this is common in low-level programming languages that do not enforce memory safety by default. And this happens in your programming. This happens in the code of the application that you are running. So some examples of this. Accessing memory after it has been freed. So when I open up Google Chrome, a memory chunk or memory block gets assigned to Google Chrome. And then once I close Google Chrome, we're supposed to give that memory back to our RAM pool. So an example, including accessing memory after it has been freed, writing beyond allocated buffer boundaries, or using uninitialized memory. So pretty much taking that memory for something malicious, and the computer or the anti-malware, the antivirus, or EDR solution thinks oh, it's used for this process, that's not malicious, but actually that malicious process is using it. So these vulnerabilities can allow attackers to execute arbitrary code, escalate privileges, or cause denial of service conditions. So yeah, and that's essentially what it's doing. Think about a buffer overflow attack, which is a memory-based attack. It's let me, spill this, allocated memory into other applications that are currently running, and then they don't run at all, right? So that's almost like we're denying you a service, which is running the application on your device. Okay, race conditions. This one's actually very cool. So it deals with time of check, time of use as well. It deals with timing of how code is executed. So the first man to discover race conditions actually did it by exploiting Starbucks gift cards. I'll show you. I always like to tell this story. First race condition, exploit Starbucks. Is this, yeah, I need to save this one because I always bring it up in class. I always got to find it. But essentially, a researcher, he just kept transferring gift card amounts back and forth until he would get it would never go down to zero essentially, So he just kept exploiting that. But, that's one of the first race conditions. So anyways, moving on. So if you can imagine, I don't know how he did it, but this is, actually how he did it. But imagine you're executing, some sort of module in your program or your code that says transfer this $5 over to this gift card. And at the same time, that gift card you're transferring the $5 to, you also transfer $5 from that gift card to the other one. So it's A to B, B to A at the same time. And what ends up happening is it never goes down to zero. So you have a gift card with 10 and then a gift card with $5. And then you keep doing that. Then you get a gift card with 15 and then you get a gift card with $10. And it keeps going up and up and up and up. That's a race condition. Now, when we say this in an enterprise, they say, oh, you may be able to exploit a race condition to replace a file after permission checks, but before it is used. And race conditions actually happen non-maliciously as well. Have you guys, especially if you worked on DoD domains, when you log in, there's so much group policy getting applied to that domain joined computer, to your user account. Have you ever logged in and you can't access things that you normally can? Like your shared drive or things like that, and you're what the hell? Let me just restart my computer. And then you re-log in, and all of a sudden you're fine. That's like a race condition. That is during the login process, during that domain join to the Active Directory domain services, something in that time, in that sequential order, didn't apply permissions correctly, and then you didn't have the correct permissions to access the objects that you usually typically do. So it's just system design. It's all development and developers. Cross-site request forgery. So cross-site request forgery attacks exploit the trust of a web application places in a user's authenticated browser. So when a user is logged in, the browser automatically includes authentication cookies with every request. Attackers can exploit this behavior by tricking users into sending malicious requests without their knowledge. So CSRF attacks commonly target actions such as changing passwords, transferring funds, or modifying account settings. So defending against CSRF, cross-site request forgery, requires verifying the requests are intentional, anti-CSRF tokens, same-site cookie attributes, and requiring re-authentication for sensitive actions. That's like, on your bank, re-authenticating to access things. Server-side request forgery. So server-side request forgery vulnerabilities occur when attackers can influence a server to make network requests on their behalf. This often allows access to internal services that are not directly exposed to users, such as internal APIs, backend APIs that maybe we don't want to expose that aren't public. So server-side request forgery is particularly dangerous in cloud environments where internal endpoints may provide credentials, configuration data, or administrative access. Because, in the cloud and within a region, that's all multi-tenant environments, like I've been saying. You have a lot of microservices architectures that there's APIs and service accounts all over, right? Embedded secrets. I've talked about this a lot. Imagine you have a script that needs an API key to access something. Let's say network automation is to access Catalyst Center in Cisco to request some information to, a show command, whatever the case may be, some logs from a Catalyst Center managed switch, whatever the case may be, and you decide to hard code that key into your source code. Don't want that. We don't want those embedded secrets because then anyone can see it, even if it's hashed. Outdated or unpatched software and libraries. So this is no different than everything we've talked about with any patch. If you're using software from a third party, a software development kit, third-party libraries, guess what? You have to patch those and update those as they come out from the vendor. That's it. End-of-life software. We've talked about this a lot. If it's an end-of-life system, there's no longer patches coming out, you need to upgrade or accept the risk and use some compensating controls. Poisoning. So this is like, critical or like common network-based protocols and applications that we use like ARP, DNS, or even DHCP could be exposed to what's called poisoning attacks. So putting false entries into our DNS, into an ARP cache, or into a DHCP pool. Well, DHCP poisoning is more like you become the DHCP server, it's kind of, anyways. So that's attacking, just those typical network protocols that we use to redirect traffic, do a man-in-the-middle attack, capture those packets, intercept communications. Directory service misconfiguration and overflows. So directory services manage identities, authentication, authorization across environment. Just think Active Directory. Think using OAuth 2.0 to a centralized identity provider, and that is your directory service that you use, like in a web application. You think enterprise, you could think Microsoft Enter ID, Intune, or Microsoft Active Directory for a full on-prem solution. So these directory services need to be configured correctly, need to have the principle of least privilege, role-based access control, contextual awareness if possible, conditional-based access. And we want to make sure that the directory services are protected. So attackers often target directory services to escalate privileges or move laterally because, again, that's kind of like our central point of all your systems, all your users, all your objects, and all your service accounts. If you can access that Active Directory domain server, you're pretty much right. Okay, buffer overflows. These occur when more data is written to a buffer than it can hold, overriding adjacent memory. Already talked about this. Deprecated functions and vulnerable third parties. So deprecated functions are outdated APIs or methods that are no longer recommended due to known weaknesses. So not necessarily, this is talking about code and like functions or a module in code, really. and you don't want to keep using it because it's just like end-of-life software. It's something that is, no longer secure. Think like using SSL 3.0, which is crazy nowadays. Think about using MD5 or RC4 Cipher. And just thinking that as code, right? Using an old school library like Node.js like version 2 or something like that, right? You probably need to upgrade eventually. So that's deprecated functions or outdated APIs, old ways to authenticate to an API. Third-party components introduce external risks into systems. Secure applications can be compromised through vulnerable dependencies. Again, talking about the software libraries, software development kits, things like that. Deserialization and weak ciphers. I'm not going to touch on weak ciphers too much. We've talked about that a lot. Just use the most up-to-date as you can that fits your organizational policy and requirements and computational resources and consumption. Now, deserialization. So insecure deserialization occurs when untrusted data is converted into objects without proper validation. Think like serialization languages like JSON, and maybe you're doing OAuth 2.0 and you need a JSON web token for it to be authenticated and secure, and you're like not doing that. Attackers can exploit this to execute code or manipulate logic. Serialized data may appear harmless but can carry malicious payloads. So hey, it's just another way to attack another vector. Confused deputy and implants. The confused deputy problem occurs when a privileged system is tricked into misusing its authority on behalf of an attacker. This often occurs in permission delegation systems. To mitigate this, you use least privileged design, okay? Implant, yes, and if you're wondering, this is the first time I've heard these terms actually used in this exam here. But I haven't been to every single fucking cybersecurity conference in industry, So maybe somewhere in some environment, these terms are used. Implants are malicious components that persist within systems, often as part of advanced persistent threats. They operate covertly, enabling long-term surveillance or control. I always thought of this as like a backdoor, like a bot or a zombie, but they say implants. So reducing implant risk requires strong endpoint security, integrity monitoring, and incident response readiness. Just saying all your defense in-depth approaches help prevent against something that's implanted for malicious use. Awesome. Let's go ahead and do our quiz. You know what I need up here, guys? A button that says go to quiz or something like that. Some options over here, like go to Google Drive or something at the top of the page. All right, question one. Okay, a company operates a public-facing web application that allows users to submit feedback through a form. So maybe some sort of injection or cross-site scripting here. Recently, security analysts discovered that attackers were able to retrieve sensitive database records by submitting specially crafted input into the feedback field. The application uses dynamically generated database queries that concatenate user input directly into SQL statements. Which solution would most effectively reduce the attack surface that allowed this compromise? So really only two mitigations we have here is input validation and parameterized queries. So let's look at our options. Implement input filtering that removes special characters from user submissions. I mean, that would work too, but maybe we don't even let them, so they're saying that's more effective maybe. Let's look at B. Use parameterized database queries for all user supplied input. Crypt database stores, that won't matter because we'll decrypt when we interact with the database. Restrict access to feedback page. No. It's between A or B. Let's read this one more time. Do a form. Dynamically generated database queries that concatenate user input directly into SQL statements. So I don't think we can do A because of this line here. So yeah, it's going to be B. Yeah, it pretty much just removes the attack, right? So yeah, you guys are right. Because if you make it a drop down, they literally can't input anything. You make it radio buttons, they literally can't input anything. So yeah, B. Use parameterized database queries for all user supplied input. Okay, question 2. An organization hosts an internal cloud service that retrieves data from URLs provided by authenticated users. During a security review, analysts discovered that attackers can supply URLs that cause the server to access internal network resources, including a cloud metadata endpoint that returns temporary credentials. Which vulnerability is being exploited in this scenario, and what control would best reduce the attack surface? Internal cloud service retrieves data from URLs provided by authenticated users. Server to access internal network resources. So we're kind of like forging something from the server side. So, and then whatever, that's just saying, okay, what the attack is. This is server side, request forgery. So whatever this is, right, whatever is going on here, that they're providing something to a user, to authenticated users. The users, if there's a hacker in there, says, here's a URL, and that URL does something that grants that server access to resources and then can return temporary credentials. That's the attack. So it's a server that's actually grabbing something from our input. So we're manipulating the server. So yeah, that's server-side request forgery. So that is D. The server is making network-based requests, right? So and that one's hard to spot. A little bit harder to spot than like cross-site request forgery because, yes, it's a user inputting a URL. Obviously there's a hacker somewhere, but when the server is originating the connection, it's kind of harder to spot. Question 3. A development team is maintaining a legacy application that relies on an unsupported cryptographic library and an operating system that no longer receives vendor updates. The system continues to function but has accumulated multiple known vulnerabilities with publicly available exploits. What is the primary risk of continuing to operate this system, and what action most effectively reduces the attack surface? All right, let's read this again. What is the primary risk of continuing to operate this system? What action most effectively reduces the attack surface? Okay, legacy applications. We're already thinking can't patch, can't update, need to compensate. Bad cryptographic library. It's legacy. Okay, so we need to compensate it somehow. So let's see. Increased likelihood of configuration drift mitigated by automated deployment models. Yeah, you think B? Yeah, segmentation. Let's read it. A guaranteed exposure to unpatched vulnerabilities mitigated by system replacement or isolation. Essentially, that's all we can do. We just need to compensate. Reduce system performance mitigated by hardware upgrades. We can't upgrade it. More RAM doesn't make it less legacy. Loss of data availability mitigated by frequent backups. Yes, you're right, Monsieur. There's really, with that legacy, there's only two things. Either replace it or you try to protect it as best you can. All right, another 100%. We're killing it, guys. Okay, what do we got left? So we only got 4 slides left. So yeah, let's go ahead and take a break. We come back, we'll go over domain 4.2.2. It's a fucking long one. We'll go over 4.3.1. Probably take another little quick break. Then finish up the last domain and domain 4 because these are kind of long ones too. And then we'll go over that some stuff that I talked about yesterday, okay? Let's go ahead and take our break. Where's that timer at? later. All right, guys, let's go ahead and continue. So domain 4.2.2, given a scenario, analyze vulnerabilities and attacks and recommend solutions to reduce the attack surface. So now we're gonna go over all the different mitigations. So let's do it. There's a lot here, and again, a lot of them that we've been over before. I'm really just gonna like glaze over it. Just like we don't need to keep beating a dead horse. And but validation, like I've talked about, is the process of ensuring that all data entering a system is safe, expected, and properly formatted before it is processed. This is in code. This is making sure that we don't accept certain input, right? The input that could be a potential injection attack or cross-site scripting attack. Output encoding. This is saying, hey, when there's an error, someone tried to access our website, we don't want to release too much information about the error that could reveal a lot of things about our backend infrastructure that attackers could use against us. So this mitigation is especially important in web applications where user-supplied data is often displayed in browsers. Without proper encoding, attackers can also store malicious scripts that execute when other users view the content, resulting in stored or reflected cross-site scripting attacks. So output encoding converts special characters into safe representations that cannot be executed by browser interpreter. So it also protects against cross-site scripting, the stored and reflected attacks as well. Okay, a safe function. So safe functions are programming constructs designed to reduce or eliminate common classes of vulnerabilities by enforcing secure behavior at the code level. So when we talked about in the past like CI/CD pipelines and the DevSecOps process and where does cybersecurity fit in, it's kind of talking about, these are some of the things where you fit in, where you say, hey, I know we're trying to get this application, pushed. We have our MVP, we got whatever, we're trying to get it to market, whatever the case may be, language and jargon we're going to use to say we need money from as a company. Our process is saying, hey, let's make sure there's just some good fundamental cybersecurity coding logic and functions in there. And this is going to go over some of those things. So atomic functions are a type of safe function that complete as a single indivisible operation. This prevents situations where part of a process executes while another part is interrupted or manipulated. So when you look at like atomic timing and things like that, it's like nanosecond synchronization. This is kind of in that same, I would say, field where this term here, atomicity, is critical in security-sensitive operations such as authentication checks, privilege assignments, and financial transactions. It just means that we need to have that good sequence and good timing for whatever modules or functions we're executing in our code. So by using atomic functions, developers protect systems from race condition attacks where attackers exploit timing gaps between operations. Memory safe. So memory safe functions protect systems from vulnerabilities related to improper memory handling. So again, that's our buffer overflow, our memory execution attacks. So memory safe functions enforce strict bounds checking and prevent access to unauthorized memory location. So some programming languages provide built-in memory safety by design, reducing the likelihood that developers will accidentally introduce memory-related vulnerabilities. And a lot of times this isn't like a malicious thing developers do. It's just in the midst of getting something to market, we start to make things work. We may leave things like memory reallocation when someone closes our application may just fall to the wayside, right? Thread safe. So thread safe functions ensure that applications behave predictably when multiple threads execute simultaneously. Something that's, I wouldn't say hard to do, but came about with modern design is with our CPUs, we wanted to say, hey, how do we make these CPUs more efficient? And we started doing something called, multi-threading, where we ran operations in parallel that gave us what looked like a more efficient system where we could do multiple things at once. So with that became the manipulation of that increase in productivity and availability. As hackers and cybersecurity follows those trends, that's always the case. Something gets better, well, someone manipulates it, right? So when thread safety is not enforced, simultaneous access to shared variables or resources can result in inconsistent state. These inconsistencies may allow attackers to escalate privileges, manipulate authentication logic, or corrupt sensitive data. Thread safe functions prevent these issues by controlling how threads interact with shared resources. Okay, security design patterns. This is just saying whatever we're developing, whatever we're implementing, from a cyber perspective, we have these design patterns. We have these common things, whether that's on-prem, in OT environments, and embedded systems, and our endpoint servers, or anywhere in the cloud, any service model, any deployment model that we must follow. If you look at zero trust, that's always my kind of framework I like to use when you get into the nitty gritty of anywhere I go, if I'm worried about security, just security, I'm not thinking about availability just yet, which is my role. I'm not thinking about how this enables business operations to make a profit. I'm just worried about security. I'm thinking role-based access control, access control, period. So principle of least privilege, hardening, reducing attack surface, a defense in depth approach, passwordless authentication if possible, looking at my boundaries and how I do network filtering, how I do network monitoring, things like that, just secure design patterns that from a small web application you build to the largest enterprise directory service that you manage, these weaknesses kind of follow the trends. They all kind of, hackers are looking for the same exploits. So security design patterns are proven architectural solutions that address common security challenges in a consistent and repeatable way. And again, this is all influenced by your organization, organizational policies, regulations, sectors, things like that, compliance. Okay, guys, we've talked about updating patching so much. I'm not gonna speed run through this, but we're just gonna, you need to patch and update your operating systems. Make sure you don't do it right away. When Patch Tuesday comes out, don't apply those patches on your Windows machines right away. That may break third-party libraries. Do it in a process. Make a process for your patches and updates. But this is a common thing that we must do as the basics of cybersecurity for protecting our enterprise. Update and patch your operating systems. And do it in a way that doesn't break things. You update and patch your software. Software engineers update and patch their libraries, their software deployment kits, their third-party integrations, whatever the case may be, update it because that fixes vulnerabilities when patches come from vendors and things like that. Your hypervisor, if you're using virtual machines, don't just patch the virtual machine that's a Windows server so you get the Windows Server patch and update. Also, your hypervisor is a concern as well because that is what is controlling all the physical allocation of resources to those VMs. So you also want to patch and update at the hypervisor level. Firmware. At the lowest level, if you get firmware that has a possible exploit, that's a big deal. It's always a big deal because inherently it's hard to detect an exploit in firmware. So if there's firmware updates available that don't break your network, that don't break your systems, you want to apply them and patch them. System images. So, this is like, what is the difference between operating systems? Well, this is just like, if I have a system image built on Windows 11 23 Hotel 2, that's 2023. And that's how I'm imaging computers. And, maybe it's time just to fix that image. So when an influx of users come in, they just get the most up to date as well. Least privilege. Again, we've talked about this at length. The principle of least privilege is assigning the right amount of permissions for you to do your job, nothing more, nothing less. This is something that's basic fundamentals in cybersecurity that is applied with role-based access control that can be applied across multiple cross-domain functions within enterprises, APIs, whatever the case may be, service accounts, object IDs or objects in Active Directory, role-based access control, all of that, you should follow the principle of least privilege. Fail secure / fail safe. So fail secure and fail safe describe how systems behave when something goes wrong. So we'll have like open, close, things like that as well. A fail secure system defaults to denying access or stopping operation when a failure occurs. That's like close. That's what it used to be called. That's what it calls in Security Plus as well. Ensuring that security is maintained even during unexpected conditions. A fail safe system places the environment to a known safe state to prevent harm. So security failures often occur not during normal operation, but during errors such as system crashes, configuration failures, or service outages. If a system fails open, attackers may gain unauthorized access simply because security controls stop functioning correctly. So that's a fail open system. Proper fail secure design ensures that authentication failures, authorization, or encryption issues do not result in unintended access. Secrets management. We've talked about this at length too. Don't embed the keys in the software. Don't make them easily available. Don't put them in your configuration files that you're storing in GitHub if possible. You want good secrets management. Your API keys, your WAN keys for your routing protocols, the encryption keys that you use, the private keys, store them somewhere secure. There's multiple different ways to do this. We talked about this. This could be software based. So they're just a piece of software like Ansible Key Vault. If you're doing Ansible, that's a great one. HSMs, hardware security modules, can help you with secrets management. You can have what is it called? Password manager. There's a name for it. I forgot. But password managers. I use something called KeyPass in my environments before, where it's like offline. That's all secrets management is. Make sure you're not intentionally exposing it. Now we get it if you're in a staging environment, like I need this to work. I don't want to integrate, a key vault just yet into my script. I just want to see if this can provision my resources and I can do infrastructure as code before I start protecting. Okay, but always get to good secrets management. Key rotation. So key rotation, we do this monthly with our, encryption devices and encryptors in the military. Key rotation is the process of regularly changing cryptographic keys and credentials to limit the impact of compromise. Just key rotation, it's just good practice. Key deletion, having good lifecycle management over the keys. Something we've talked about a lot. Okay, least function sets functionality. Kind of falls in line with principle of least privilege, but it doesn't just lean into access control. But there's also this just like simple hardening, kind of just puts a name to it. So least functionality is the principle of reducing a system to only the features, services, components that are absolutely necessary. My entire time in IT, we just call this hardening, right? But I like that they're putting a name to it. It's kind of like least privilege, least functionality. It's like if I'm deploying a DHCP server, sorry, I feel like I'm talking fast. Sorry, guys. If I'm deploying a DHCP server, it should just do DHCP. We shouldn't have all these open functionalities and open ports on it. It's like one service, one application per server, per back end. That's least function / functionality. Defense in depth, something I've talked about a lot. This is just a security strategy that layers multiple independent controls ranging from policy, physical security controls to the logical and technical controls that you place on your entire enterprise to achieve organizational risk management, controls, frameworks, compliance, all that. Dependency management. So dependency management focuses on controlling and securing third-party libraries, frameworks, and components used within applications. Modern software relies heavily on external dependencies, which can introduce vulnerabilities outside the organization's direct control. Okay, code signing, I've talked about this a lot. This just allows you to have integrity, authenticity by putting a digital signature or adding a message digest file onto your code that may be public or available to the enterprise, internal users, even external users. Encryption. Encryption change plain text into ciphertext, and this protects a lot of things. All data at rest, all data in transit, and a lot of your key services, things that could be critical, you want to apply encryption to it. I'm laughing because, it's... We talked about that so much, encryption, but they want to say it again. Indexing, we went off indexing when we went over SIGN, but this is kind of more of a holistic level of indexing across an enterprise. So indexing determines how data is stored, organized, and made searchable within systems. Improper indexing can expose sensitive information by making it easily discoverable. Attackers often exploit indexing to enumerate data and identify valuable targets. If sensitive fields such as credentials, personal data, or internal identifiers are indexed without restrictions, attackers may retrieve them through search queries or application features. Okay, then allow listing or whitelisting. I think I talked about this day 2, but essentially this is saying, hey, allow listing can be applied not only to software downloads, could be to scripts, could be to remote executions, whatever the case may be. Allow listing is a process of doing access control that says this is allowed and everything else is implicitly denied. That's allow listing. And the easiest way to think about this is when it's like downloading software or applications onto your enterprise. You have a whitelist that says, here are all the things that are approved. There's an implicit deny after that. And if you, the user, want something added to that allow list or to that whitelist, put in the proper paperwork. Let's go through some sort of change management, make sure it meets organizational risk policy, and then go from there and see if it can be allowed to the whitelist. Awesome. Let's do our quiz. That one again too. Oh no, here it is. Take the main quiz. Question 1. A security team is investigating a breach where attackers exploited a known vulnerability in a third-party library used by an internal application. The vulnerability had been publicly disclosed months earlier, but the application was never updated. Which mitigation would have most directly prevented this attack? Okay, security team is investigating a breach where attackers exploited a known vulnerability in a third-party library used by an internal application. Yeah, no, third-party library. Okay, so dependency. Just read it. Just always trying to find like the, where it pretty much gives you the answer. Third-party library. Yeah, I'm going to go with D as well. Yeah, dependency management. Question 2. Let's see. An organization discovers that several internal services are running with administrative privileges even though they only require access to a small set of files and APIs. Security leadership is concerned about the potential impact if one of these services is compromised. Which mitigation best reduces the potential damage in this situation? Privileges, small set of files and APIs. This is least privilege. Yep, this is the principle of least privilege. Okay, question 3. A development team is reviewing a web application that allows users to submit text, which is later displayed to other users. The application properly validates input by restricting length and allowed characters. But security testing shows that attackers can still execute malicious scripts when viewing stored content. Which mitigation would most effectively address this issue? Okay, let's see. User submits text, which is later displayed to other users. The application properly validates input. So we're doing input validation. The application properly validates input by restricting length and allowed characters. But security testing shows that attackers can still execute malicious script when viewing stored content. So stored content, that's like our encoded content. I think it's what's trying to tell us. Which mitigation would most effectively address this issue? Yeah, I think it's trying to fool because input validation is happening. It's still input from users. So the only thing that can happen with this, whatever application this is, its front end, is A, apply output encoding at the point where data is rendered. Let's read this. This scenario describes a classic case where input validation alone is not sufficient to prevent cross-site scripting attacks. Even though the application restricts input length and characters, the stored data is still being interpreted as an executable code when it is rendered in a browser. Output encoding is specifically designed to address this problem by converting potentially dangerous characters into safe representations at the moment the data is displayed. This ensures the data is treated as text rather than executable instructions. Okay. Yeah, so pretty much like, we put HTML brackets in to try to do an injection attack to send like JavaScript somewhere. This is saying input validation, if it doesn't stop that, we're just going to take that as text no matter what, right? So cool. Output encoding. Makes sense. Okay. Let's go ahead and do our quiz now. Or sorry, domain 4.3. Okay, so now going over domain 4.3.1, given a scenario, apply threat hunting and threat intelligence concepts. So here are all the objectives we're going to go over. Now when we get to these guys, these rule-based languages, I'll just be honest with you. I've never used them in my day-to-day. We just never really had to. So this one I won't have a lot of examples for you. So I just apologize up front. This is the first time I'm teaching this class, so I'm just kind of like, some concepts are even new to me, even though I daily work with our cyber team, whatever, But anyways, just want to throw it out there. Okay, so let's go over this now. So internal intelligence sources. So adversary emulation engagements. So internal intelligence sources come from within the organization's own environment. These sources are highly valuable because they reflect real systems, real users, and real activity. Internal intelligence is often more actionable than external intelligence because it directly relates to the organization's infrastructure. So imagine, we're subscribed to threat feeds, and that threat feed's from RHEL, because we have a bunch of RHEL servers. That's good. It lets us know about the entire threat landscape for the operating system we're using. But like an ACAS scan or a Nessus scan on our actual Rails servers may tell us a little bit more on the spot because maybe we configure our Rails servers in a way that is unique. So adversary emulation involves simulating the behavior of real-world attackers in a controlled manner. This is, our internal red team, blue team operations, So that's adversary emulation. The purpose of this is to see how the purpose of that is just, hey, what do we think, an ATP would attack? And maybe we're using things like the Matter attack framework, the cyber kill chain in this kind of simulation event or this emulated event. And we can also train our blue team in that way. Like, do we have the proper monitoring and things to catch this, fake attack or emulated attack? Internal reconnaissance and hypothesis based. So internal reconnaissance refers to collecting and analyzing data generated by the organization's own systems. This includes logs from endpoints, servers, network devices, and authentication systems, cloud platforms, and applications. The enterprise, right? That's what we're saying here, internal reconnaissance. So threat hunters rely on internal reconnaissance to establish a baseline of normal activity without understanding what normal behavior looks like. It is impossible to identify anomalies without understanding what normal behavior looks like. So internal reconnaissance allows hunters to spot unusual patterns. This is like creating a behavior baseline again. Hypothesis-based searching is the foundation of effective threat hunting. Instead of searching blindly, analysts begin with a logical assumption based on known attack techniques. What a great thing to learn in at the professional level cert, right? Hey, don't just start looking at threat feeds and saying this kind of execution happened and then you go look for it for weeks, right? Maybe we take a hypothesis-based approach that says our environment may or may not have this, so that's what we're going to go look at. That's all that's saying right there. It's just be smart when you're doing your reconnaissance or intelligence, OSINT, threat hunting activities. Okay, honeypots and honey nets. So these are our decoys that we use to try to entice an attacker. So a honeypot is a system intentionally designed to appear vulnerable or valuable to attackers. Again, it leads to nowhere. It's just, hey, we want to get an attacker into our honeypot so we can start learning its TTPs. A honey net is the same exact thing, but it's an entire ecosystem, an entire fake enterprise or multiple VMs, multiple VNets in a cloud environment. Same exact thing. It's exposed, it's vulnerable, an attacker hacks it, and then we monitor that and we kind of reverse engineer their TTPs like, okay, here's how they're doing this, here's how they're doing lateral movement. And it's supposed to kind of mimic your real-world production, not entirely, obviously, but it's supposed to give you some sort of insight if it does actually end up getting attacked to how your real production enterprise environment would get attacked as well. All right, UBA, talked about this a lot, but it is an intelligence source. It is user behavior analytics. This is, again, looking at behavior baselines, and that's pretty much it. And for threat hunting, looking at behavior baselines can help us see when things deviate. External intelligence sources. So this is OSINT. This is going to be external threat feeds. Dark web monitoring, yeah. So if we want to look at underground forums, but OSINT is just, it's open source intelligence collected through publicly available sources. You could have a whole team dedicated to this. Now, I don't know what, civilian corporation does this. Maybe they do, but, this is a role in the DoD as well. This is looking at blogs. This is looking through forums online. Then dark web monitoring is the same thing, just on the dark web, and it can be a little bit more malicious. After a major data breach, we may search the dark web for, that leaked PII or PHI, whatever the case may be. Okay, ISACs. So ISACs, let me bring this site up here for you guys. So ISACs are for multiple different sectors, right? So it stands for Information Sharing and Analysis Center. Hold on. And there's this National Council of ISACs that pretty much says, hey, we're going to do research and publish things based off your sector or your field. So Information Sharing and Analysis Center. So you can become a member. You can look at reports. for all the different ISACs. So you see IT, retail and hospitality. That's all it is. Just another way to get more information if you're a cybersecurity professional. Now, there's so much threat intelligence feeds you can subscribe to. You know, when I see my cyber guys, they're always either learning like their new rels, they're in like webinars from industry professionals, and they usually have some sort of threat feeds that are getting sent to them. There's really not to say one is the best or one isn't the best. These ISACs is one. They give annual reports. You know, you can become a member. You can become a contributor. It really just depends on what you feel is the best one for you. And then reliability factors. You know, and again, which one do you feel is reliable? You know, I just like reading the NIST documentation. I like reading the CVEs as they come out. And what gets posted on CISM. You know, that's the most that I honestly do when it comes to threat intelligence feeds. Not that that's good or bad, but I know in big organizations, like if you're a huge Cisco firewall organization or Palo Alto, you may want to subscribe to their threat feeds because that's maybe more like for you exactly, which would be more important for like day to day. You know, I'm not trying to learn, I'm trying to make the business successful. That may be a good intelligence feed, you know, a vendor one. Okay. Counterintelligence, operational security, and then going over threat intelligence platforms. So counterintelligence focuses on protecting the organization's security operations from being observed or exploited by adversaries. Operational security ensures that sensitive details about detection capabilities, response procedures, and defensive tools are not exposed. Threat intelligence platforms are centralized systems used to collect, manage, and analyze threat intelligence from multiple sources. So this is just kind of, it's almost like what our SIEMs do, aggregating from multiple threat feeds and sources. Okay. Counterintelligence, operational security, and tips and third-party vendors. Why did I repeat this slide? Like I said, okay, whatever. We'll go over third-party vendors. Many organizations use third-party vendors to supplement their intelligence programs. These vendors provide curated intelligence feeds enriched with analysis and content. So kind of like I was talking about, like if I'm a Cisco firewall shop, you know, maybe I just want to look at those Cisco firewall threat feeds from the vendor. You know, that may be more specific to me. Okay, IOC. What is an IOC? This is called the indicator of compromise. Now, if we were in my CYSA class, we could go through all the different types of indicators of compromise across the multiple threat vectors. But really at a high level, we're just saying, you know, what are the big ones and do you understand what an indicator of compromise is? This is just saying when we're monitoring, if we see multiple like DNS sessions that have high data payloads going to an external IP that we don't recognize, that's like not a DNS server, that's maybe an indicator of compromise for data exfiltration. That's really all we're saying, right? And understanding this definition is, hey, through my research, through my threat intelligence feeds, through me looking at domain blacklisting or having that integrated into my firewall that's doing my IDS and IPS for me, I see that this user has constant connections to this bad external IP. It's an IOC. Now, indicators of compromise do have its own little ecosystem. So we're going to talk about STIX and TAXII. So STIX, the Structured Threat and Information Exchange, is a standardized language used to describe cyber threat intelligence in a structured, machine-readable format. So this is like you can integrate STIX again into like your cybersecurity appliances. It's still around. It's still a thing. You know, I've been teaching this for a while, since like 2018. Even when I was like in the Army, I taught like CASP, Security Plus and stuff. And as these new certs came out, like CYSA, and they've been talking about STIX this whole time. I still haven't seen it in like active use, but again, my only sector has been DoD. But we'll talk about it. Instead of sharing unstructured reports or free-form text, STIX defines how to represent indicators, threat actors, malware, attack patterns, and relationships between them. And again, this is into like a machine, not necessarily for you. It pretty much is just XML. Like you actually look at STIX, you go look it up online. It just looks like XML. It's like a markup language. So STIX enables defenders to understand not just individual indicators, but the broader context surrounding a threat. And then TAXII is the architecture for it. This is like the servers, receivers, clients, things like that. So TAXII enables automated, secure, and authenticated sharing of threat intelligence. So organizations can subscribe to TAXII feeds from intelligence providers, industry groups, or government agencies. Okay, rule-based languages. Let's go through this. Sigma is actually like YAML-based, but let's just read them. Sharing intelligence is only valuable if organizations can operationalize it, use it operationally. Rule-based detection language allows defenders to convert threat intelligence and attacker knowledge into detection logic that security tools can execute. So let's go through the different rule-based languages. So Sigma. Sigma is an open platform agnostic rule format used to describe detection logic for log data. Instead of writing detection rules for a specific sign product, Sigma rules define conditions in a generic way that can be translated into queries from multiple platforms. So think like I got Splunk and maybe I have some cloud-based sign. I can use Sigma across both of those. Yara, so yet another recursive acronym, is a rule-based language designed to identify and classify malware. So Yara rules define patterns found within files or memory, such as strings, byte sequences, and structural characteristics. So more like the computer level when it comes to like strings or byte sequences. Unlike simple file hashing, Yara can identify families of malware even when attackers slightly modify the code. Threat hunters use Yara to scan systems for known malware patterns, detect reused code across campaigns, and identify new variants of existing threats. Rita is a tool designed for analyzing network traffic to detect suspicious communication patterns. It focuses on identifying behaviors associated with command and control activity, such as beaconing, which is like, kind of like, hey, I'm here, I'm a botnet. Long-lived connections, like persistent data exfiltration connections or backdoors, and unusual communication intervals. Okay, Snort is a network intrusion. I know this one's like, I see this a lot like in YouTube videos, honestly, with like cyber security professionals. So Snort is a network intrusion detection and prevention system that uses rule-based logic to inspect network traffic in real time. Snort rules define patterns that indicate malicious activity, such as exploit attempts or protocol abuse. All right, then TTPs. We're actually looking at the definition. TTP stands for tactics, techniques, and procedures. We talked about this at length when going over the MITRE attack framework. So this is just saying, hey, during threat hunting activities, one of our main goals is to learn the TPPs of our adversaries or potential advanced persistent threats. So yes, TTPs. Very common thing just in cyber in general. I mean, in IT in general, right? Our tactics, techniques, and procedures. Okay, let's do our quiz now. Our domain 4.3.1 quiz. Okay, question 1. Let me pop out the chat real quick. Hold on. Okay, hold on. Sorry, guys. A threat hunting team wants to move beyond relying on file hashes and IP addresses, recognizing that attackers frequently change these artifacts. Instead, the team wants to detect attacks based on how adversaries operate during different stages of an intrusion. Which concept best supports this goal? Oh yeah, they're TTPs. We're trying to look at their TTPs, right? So yeah, that's going to be A. Question 2. A security analyst is conducting a proactive threat hunting exercise. Instead of reviewing logs randomly, the analyst starts by assuming that an attacker who gained access through phishing would attempt to move laterally using built-in administrative tools. The analyst then searches authentication logs, endpoint telemetry, and PowerShell execution records to confirm or disprove this assumption. That's probably the word we're looking for here, just looking at the answers. Which threat hunting concept is the analyst primarily applying? So, we're searching, and it's hypothesis-based searching. Question 3. An analyst is investigating suspicious network traffic and notices that a workstation is communicating with an external server at very regular intervals. Even though the destination address changes frequently, the analyst is less concerned with the specific IP address and more focus on the communication pattern itself. Which tool or approach best supports identifying this type of behavior? So really the only answer here is B or C, right? Because snort and read are both our network ones. But I think since we're looking at communication patterns itself, it's going to be C. So yeah, the key detail in this scenario is the focus on communication behavior rather than specific indicators such as IP addresses or domains. RITA is designed to analyze network flow data and identifying patterns commonly associated with command and control activity, including beaconing and consistent communication intervals. Oh, we got 5 questions here. Okay. Question 4. A security operations team receives a feed of threat indicators from an industry partner. The indicators include information about malware, associated threat actors, and relationships between attack techniques. The team wants to ensure this intelligence can be automatically processed and consistently interpreted by multiple security tools. Which technology is best suited for representing this threat intelligence in a standardized machine readable? Okay, yeah. So STIX. It sticks. Machine readable kind of gives it away there. Question 5. An organization deploys a system that has no legitimate business function but appears to be a valuable internal server. Security teams monitor this system closely and treat any interaction with it as suspicious. Over time, analysts use the data collected from this system to better understand attacker tools, techniques, and movement within the network. Which internal intelligence capability is being described? Just a system, no business function, but appears valuable, and we want people to attack it. Yeah, that's going to be a honeypot. Hell yeah, let's go, 100%. All right, guys, let's take our last break for class, and then we'll finish up domain 4. We'll come back at like 7:05, and we'll be done. And then I got to go over a few more things with you guys, just to kind of wrap up and close class out, and then we'll be good. Okay, so finishing up domain 4. So now we're going to go over domain 4.4, given a scenario, analyze data and artifacts in support of incident response activities. So we're going to go over malware analysis and reverse engineering in this section. And in red is everything we're going to go over in these slides. So malware analysis. Malware analysis is the process of examining malicious software to understand how it works, what it is capable of doing, and why it exists. In incident response, malware analysis is not performed out of curiosity, but to answer urgent operational questions, such as how the malware entered the environment, what systems are affected, and what damage may have already incurred. So from an incident response perspective, a malware analysis helps determine the scope and severity of an incident. And then also after analysis, we can put that as part of our signature file to ensure that that malware doesn't attack us again, or if it does, we can remediate automatically. Malware detonation. This is a controlled execution of malicious software in a safe, isolated environment. Think of, we know there's malware, we haven't executed it yet. We put it in a sandbox environment, in a testing environment. This could be an isolated virtual machine on a host device that's already isolated in itself. And during that detonation, we gather analysis from it. So, it's critical that malware detonation occurs only in controlled environments, such as virtual machines or dedicated sandbox systems. IOC extraction. So indicators of compromise, or IOCs, are specific pieces of evidence that suggest malicious activity has occurred or is occurring. Common IOCs include file hashes, malicious IP addresses, domain names, registry keys, file paths, and process names. Once extracted, these indicators can be shared with security tools such as IDS, EDR, and SIEM solutions to help our overall threat vector monitoring or attack surface monitoring. Sandboxing. So again, this is how we do the malware detonation. Sandboxing is just any really application or even virtual machine that allows us an isolated environment that can then be destroyed, and we're trying to limit the risk of VM hopping there or sandbox jumping. And then it's not foolproof. Some malware may be configured to detect that it's running in a sandbox and remain dormant, or try to do sandbox escape. Code stylemetry. Hopefully I'm saying that right. It's a study of coding style characteristics to identify similarities between malware samples or attribute them to specific developers. This is just advanced persistent threats are humans at the end of the day. It's not AI yet. Well, maybe it is. But malware is developed by humans, and everyone has their own style of development where, there's so many different ways you can write a function in a coding language that achieves something. There's some that is more efficient than others, and designers essentially have their own style, or code developers, software engineers have their own style. So if we're in a shop that does reverse malware engineering or malware analysis, where we can actually get the source code, we can kind of figure out or relate that maybe to a team or an actual hacker. Variant matching. Variant matching is the process of determining whether a malware sample is a modified version of an existing malware family. Attackers frequently reuse code while making small changes to evade signature-based detection. Because that signature-based really is just a hash of that specific malware. But think about if we could change that malware, that virus just a little bit, do our systems still detect that, right? If it pretty much, they just evolve it in a way. It's kind of like viruses in real life. I just thought about that now. It's a good, metaphor, just how viruses adapt, to our white blood cells attacking. Anyways, but by recognizing variants, responders can apply existing knowledge about behavior, persistent mechanisms, and remediation steps. It's essentially saying, okay, just because you change something about your code doesn't mean I don't know how this malware will either encrypt my drives to do ransomware or do lateral movement. I do know, so I may have a run book and a playbook already ready for this type of malware, even though my anti-malware or EDR didn't immediately contain you. Because our behavior-based heuristic analytics should then help us with that, right, if it evades signature detection. Code similarity analysis compares malware samplers to determine how close related they are at a structural or logical level. Analysts may compare control flow graphs, opcode sequences, or function call patterns to identify similarities. These techniques allow responders to detect shared development frameworks or toolkits even when the malware has been extensively modified. Malware attribution is the process of associating malware with a specific threat actor, group, or campaign. Attribution is inherently difficult and often based on probabilities rather than certainty. So attribution may involve examining code reuse, infrastructure overlap, targeting patterns, and operational behaviors. So a good example is repeated use of the same command and control servers or consistent targeting of specific industries may suggest a common actor. Kind of like we've just been talking about, right? Like how do we start attributing this to maybe a popular advanced persistent threat team? Or yeah, if they're doing beaconing or command and control to a server that is well known, it's like, well, that kind of falls in line with these TTPs of this kind of adversary or advanced persistent threat actor. Reverse engineering. If you're able to successfully do reverse engineering, you can get paid a lot of money. But it's just a process of analyzing software to understand how it works without accessing to its original source code and maybe even recreating it. So, yeah, this is a highly skilled thing too as well. And reverse engineering is often required when malware is highly evasive, destructive, or capable of hiding its behavior during detonation. Disassembly and decompilation. So disassembly is the process of translating compiled machine code into assembly language that closely reflects processor instructions. This allows analysts to see exactly how malware interacts with system resources at a low level. Decompilation attempts to reconstruct higher level source code from compiled binaries. Although decompiled code is imperfect, it is significantly easier to understand than raw assembly. And then we have binary analysis. So binary analysis focuses on compiled executable files rather than source code. Since most malware is distributed as binaries, this form of analysis is essential for real-world incident response. Key areas of focus include imported libraries, embedded resources, and executable sections. We have bytecode analysis. So bytecode analysis applies to malware written for environments that use virtual machines such as Java or .NET. Bytecode represents an intermediate form between source code and machine code. Because bytecode retains more structural information, analysts can more easily reconstruct program logic. Volatile storage analysis. So volatile storage refers primarily to system memory or RAM. Memory analysis is critical during live incident response because many malicious artifacts exist only in memory. So that's why we do like a lot of memory dumps or hex dumps when we're like doing digital forensics like on phones or systems because we want that most volatile stuff first. It's kind of like the order of volatility is what it's called. Memory analysis can reveal running malware processes, injected code, decrypted payloads, and active network connections. Then we have non-volatile storage analysis. So this is going to be things that are in like our solid state drives, other persistent systems, maybe external media. If we know malware, like, I don't know, there's a USB connected and, you know, we think the malware originated from that. It was storing things in that USB, whatever the case may be. That's non-volatile storage analysis. We don't need to do this as quick because it's non-volatile, so it's in storage. So whether it's today, a week, a month from now, we'll always be able to analyze that. Unlike memory or volatile analysis where we need to be in a runtime environment, and if we shut it down and restart it, we may lose some of those processes that we're executing in the malware. Network analysis focuses on examining traffic between systems, looking for that command and control, data exfiltration, or updates. We talked about this at length as well, how we do network analysis, so we're not going to hit on it again. Host analysis, looking at the host records, the connections from the host as well. Host artifacts provide insight into user activity and attack behavior. Maybe we have EDR, XDR installed on there, the event viewer logs, whatever the host we have, var/logs in a Linux device. Okay, let's do our quiz. Whoa, what happened here? There we go. Okay, domain 4. What the hell? I don't know why this happened in the later sections. I know I made quizzes for everything. Yeah. There we go. Question 1. During an incident response investigation, analysts collect system memory from a compromised server before shutting it down. Which type of evidence are they most likely attempting to preserve by doing this? System memory. Yeah, so yeah. Malware processes and encryption keys. Stuff that is essentially in memory, right? It's volatile. Question 2. An incident responder is attempting to determine whether a newly discovered malware sample is related to a previously identified threat group. The responder compares control flow structures, encryption routines, and coding habits across multiple samples. Which analysis technique best supports this investigation? Yeah, the only one on there, right? Code stylometry. Hopefully I'm saying that right. I'm like hooked on phonics over here. Okay, question 3. During an active security incident, an analyst captures a suspicious executable and executes it in an isolated virtual machine. The malware creates registry entries, opens outbound network connections, and installs a scheduled task for persistence. What incident response technique is being used in this scenario? It's detonating it. So it's putting it in an isolated virtual machine and trying to see. So that is B. And we don't need to do bytecode analysis or anything like that, or reverse engineering, because we see it, right? It actually detonates. So awesome. Another 100%. Okay, guys, let's do our final slide here. I'm trying to keep motivation for you guys. I don't know if you can tell in my voice. I'm like, not that I'm ready for this to be done. Of course, I've enjoyed teaching you guys, but, it's Friday, 7:20. I'm sure you guys got lives too, maybe wise kids, stuff like that. So we'll try to finish this up and do what we need to do to wrap up class. Okay. So now we'll be going over domain 4.4.2, given a scenario, analyze data and artifacts in support of incident response activities. We're going to be going over metadata analysis and hardware analysis. And then everything else here in red. Okay, metadata analysis involves examining contextual information that describes data rather than the data's actual content. While metadata does not typically reveal messages, bodies, or file content, it often exposes critical details such as who created something, when it was created, where it originated, and how it has been modified. So attackers frequently attempt to hide or alter primary evidence, but they often overlook metadata. So kind of from the attacker's perspective, if we don't get rid of that metadata, it gives the blue teams and those SOC analysts, more things to look at. Email header analysis. Email header analysis focuses on examining the routing and authentication information embedded in email messages. So phishing and business email compromise attacks often rely on spoof sender information. While the email may appear to come from a trusted source, header analysis can reveal discrepancies such as mismatched domains, failed authentication checks, or suspicious relay servers. Just somebody trying to make it seem like it's coming from a legit domain. During email header analysis, we can kind of detect that. Image metadata analysis involves examining information embedded within digital image files. This metadata may include timestamps, device information, geolocation, and editing history. So just what metadata is. So in incident response, image metadata is useful for validating the authenticity of screenshots, photographs, or scanned documents. It can help us with like chain of custody, things like that, especially in like digital forensics. Audio and video metadata analysis. So audio and video files contain metadata that describes how and when recordings were created. This may include recording device details, software used for editing, codec information, and timestamps. Such metadata provides insights into whether recordings are original or manipulated. File and file system metadata analysis. So file system metadata refers to information maintained by operating systems about files and directories. This includes timestamps for creation, modification, and access, as well as ownership and permission settings. During incident investigation, file system metadata helps identify when malicious files were introduced, how they were modified, and whether attackers attempted to hide their actions. By correlating file system metadata with logs and network activity, analysts can reconstruct attacker behavior. All right, data recovery and extraction. So data recovery and extraction techniques are used when attackers attempt to delete or destroy evidence, and most systems deleting a file does not immediately remove the data from storage though. So recovered data may include deleted files, fragments of overwritten content, or artifacts stored in unallocated disk space. Like I said, that real world example I had, to totally delete something, you usually need like third-party applications, like usually just on the system itself. there's going to be a way to recover. Threat response. So threat response refers to the actions taken to mitigate and neutralize an active or confirmed threat. Effective response includes isolating affected systems, disabling compromised accounts, blocking malicious network traffic, or removing persistent mechanisms. Incident response. So how well do we do incident response, and how fast do we get to the eradication and recovery phase of incident response? Preparedness exercises. So do we know how well our incident response is? Do we know if everyone knows their key roles and responsibilities? And do we have the correct SOPs established? So this is tabletop simulation exercises. Timeline reconstruction. So maybe in the lesson learned phase of like incident response, this is the process of organizing evidence chronologically to understand how an incident unfolded. And also we could do this to see how we did our incident response as well. So not only is it going back and getting like kind of part of like root cause analysis, we kind of do this in, but in the lessons learned phase as well, we do timeline reconstruction. I've done this a lot, like not for incident response, but just like when we were like implementing a change, let's say in the network, and it didn't go as planned, I start, just like mentally, maybe like written down on my computer, like, okay, at this time we noticed this happening, this user having these issues, and this is what we did on this network device that changes, and here's how we did our debugs and yada yada, things like that. It's very important we do that in an AAR process. Okay, root cause analysis. Root cause analysis seeks to identify the fundamental reason an incident occurred rather than focusing only on symptoms. Without this analysis, organizations risk repeating the same mistakes. An incident may be triggered by malware or a compromised account, but the root cause may involve weak policies, insufficient training, or misconfigured systems. Cloud workload protection platform. This is a new thing for me as well when I was making these. So a cloud workload protection platform provides security monitoring and protection for workloads running in cloud environments. These workloads include virtual machines, containers, and serverless applications. Now, like when I say new, this is like, it's not a CompTIA word. I'm sure it's an industry, but it's like Azure Sentinel, Microsoft Defender. There's already things that do this. I think this is just kind of like the vendor agnostic way to describe how old GCP, AWS, Oracle, and Azure may do this inherently already. Resources that you can rent from them to do this. When I say rent, just a cloud resource, right? Because it's operational expense. From an incident responder perspective, CWPPs provide visibility into runtime behavior, network activity, and system changes that may otherwise disappear when cloud resources are terminated. Insider threat. Talk about this a lot. An insider threat occurs when a trusted individual misuses authorized access to harm an organization. And we need to be trained and aware of what insider threats look like and how they start building. Okay, last quiz. We better get 100 on this one too. Okay, question 1. During an incident investigation, a security analyst receives an email that appears to come from an internal executive requesting an urgent wire transfer. What type of analysis would be most effective to determine the true origin of this email? Yeah, it's going to be email header analysis, right? Oh, let me scroll down a little bit. Social engineering technique there, trying to use urgency and trust. Question 2. After containing a security incident, an organization wants to understand why existing security controls failed and how to prevent a similar incident in the future. Which activity best supports this goal? Yeah, root cause analysis, yep. Question 3. An organization discovers that a compromised IoT device continues to behave maliciously even after being rebooted and reimaged. Which technique? Okay, what? This doesn't seem. We definitely didn't go over that though. Masood, you must. Yeah, you watched Dion Training's videos. You must remember that from that. But I must have missed that in my slides. I don't remember going over joint test action group analysis. Okay, well I'm gonna hold on. I'm gonna mark this so I can fix this for others. Which technique would be most appropriate for determining whether malicious code exists at the firmware level? Yeah, it's C. Let's read the explanation on that. Okay, so when malicious behavior persists after a device has been rebooted or reimaged, this strongly suggests that the compromise exists below the operating system level, often with firmware. In such cases, traditional software-based analysis tools may not provide visibility into malicious components. JTAG analysis allows investigators to access the device's memory and firmware directly, bypassing the operating system entirely. Awesome. Sweet, guys, another 100%. Let me turn off recording. Give me 1 second.